And okay, let me just put this on presentation mode.
Today you're going to be all the
No,
no
half
time.
morning.
Okay. Should I?
Oh, I forgot to say something. I'm just realizing it now, but I think the challenge may have a mistake because it says the coordinates south 2 times and not south north. So
Okay, let me check that on the interval. If you
okay.
okay, if you can put that on chat for me so I won't forget, please. Because I don't have my computer right now because it's presenting. So during breakout,
I can use mine.
I can. Okay, I'll try to see it now.
A little bit different than yours.
I sent on the chat how it says. It says like this. So one of them has to be north.
Okay, I'll check it. Thank you.
Aqui, ó. Tô tirando só a câmera aqui, para você ficar à vontade. So, good morning for you. Sorry about being late today, but I think it was good because I have the opportunity to solve some doubts with Livia. Okay, so today we're going to talk about observations, observed data. And this is the main topics, types of oceanographic and climatological data. We're going to talk about the main classes of oceanographic and meteorological data that you have, the in-situ ones and the remote sensing ones, the source of publicly available data, and why data is so important for us that deals with ocean modeling, okay? Basically because of this phrase that is there in the screen, to validate model results. But we're going to talk deeply about this theme in the class of today. So just a quick reminding of the concepts that you learned and that you saw together with Livia in the class of yesterday. How, why is so important to work with ocean modeling? Because they give to us the knowledge of ocean dynamics at different spatial and temporal scales, and many other goals, of course. But this is one of the main goals that why it's important to work with ocean models and how they work, basically, okay? You have some input data. I'm not, the input data that you can call initial or boundary conditions. Yeah? You learned this concept in the class of yesterday. Of course, there are not only this kind of information. I only give you some examples like the wind that flows over the sea surface, the radiative fluxes, temperature and salinity, and sea surface height. And remember that some of these forcing fields are two-dimensional, and the other ones are three-dimensional fields, okay? So you took this data and force the model. This is the way that we talk about applying these fields to force the model. And then inside the model, what you have a set of physical mathematical equations that describe the ocean phenomenon that you want to represent using your model, okay? Of course, this set of physical mathematical equations, as Livia showed to you yesterday, is discretized in space and time. So we take the infinitesimal derivatives and transform them in discrete differences, okay, in time and space. And you use the lateral and surface and bottom boundary conditions together with other kinds of parameterizations, such the one that I put on the screen, the turbulence closure schemes. This parameterizations is trying to solve the subgrid scales processes that you cannot solve directly with the set of physical mathematical equations that you have in your model. So you need to parameterize this phenomena using, for example, turbulence closure schemes models. So you apply this, and then, okay, you have as an output, for example, coherence fields, three-dimensional coherence fields, temperature fields, three-dimensional temperature and salinity fields, and many other variables, okay? Diagnostic and prognostic variables as a result. So everything is okay. No, you need to validate, you need to trust in your model results. And how can I trust in my model results? Using observations. That's why you're going to have, it's so important to have the class of today, okay? So you need to know how can you use observed data in an integrated way with computational numerical models that we call here physical models. When I said computational numerical models, I put in this box not only oceanographic models, but meteorological models, climate models, okay? All of these models that try to represent to us geophysical fluids dynamics, okay? Please feel free to ask any questions if you need, interrupting me or put in the chat, okay? So we'll have observations and modeling. And how can we relate observations and modeling? Well, first of all, we need to, as I said to you, we have basically two classes of data. The in situ data sets that came from in situ sensors. We're going to see a lot of in situ sensors in the class of today. And we have the remote sensors, okay? The sensors that acquire the data in a distance of the place that you want to acquire the information. For example, satellite is a kind of a remote sensor. Radar, okay, that you have in airports, for example, or over vessels, ships, it's another kind of a remote sensor, okay? And modeling. What's a kind of modeling? The models that we're talking today here, that we're talking along our course, the atmospherical models, the ocean models, the climate models, okay? And you have all of this, the observations and modeling must be integrated. And how can I integrate observations and modeling? Basically in two ways. You can use as to validate, to validate or evaluate the results that you are generating with your model, okay? There is the validation processes. So basically, you generate your results in one point, and then you compare. You do a comparative analysis using, for example, statistic tools or any other tools, mathematical tools, to compare if your modeling results is, how can I say, is the same, or almost the same, or similar as your observation pattern in time and space on the region you want to apply your model, okay? And the other way is the assimilation process. What is assimilation process? I think that Liva told you a little bit about these processes in the class of yesterday. Is the process where you use observations not only after the modeling processes, but along the modeling process, use data, observation data, in an interactive way together with the numerical model. The idea is basically to push the model results to the observations that you have in space and time, okay? I'm going to show a little bit better about these processes in the class of tomorrow, okay? But the main idea is to use, during the model processes, the observations to be assimilated in computational model to trying to acquire a better representation of the ocean and atmospheric dynamics. And now, not now, but maybe a decade or a little bit more, a little bit less ago, we have data science. Data science directly applied for Earth observations, okay? So data science is a very powerful tool that you can use only with the observations that you have, or together with the modeling results that you have. If you have a very good run of your model that represent very well the state of the ocean in one region, you can use these model results as a database to be used in data science, because data science algorithms, as the machine learned ones, we'll do the following. We'll take these data sets, learn with these data sets, and learning with these data sets, these ocean data sets, it could be possible to do, for example, the forecasts of the many different ocean variables, okay? This is what I told you about the process of data science. It was very simple. It's not so simple as I'm saying to you, but in essence, what you have in data science, the application of this tool is like that, okay? Let's go. So now let's go and start about observation. So as I said to you, we can divide in remote observation and in situ observations. But before I start to talk about observations, I'm going to talk about a very important equipment that you need to have in oceanography. There is the oceanographic vessel. Okay, so here in screen you see different types of oceanographic vessels, different photos of oceanographic vessels, the most modern ones and the less modern ones vessels, okay? Basically, these oceanographic vessels must have a stern or a side deck to facilitate equipment launching operations. We're gonna talk about this kind of equipment and sensors that you use in oceanography after this slide. But you need to have this stern to just to put the equipment in the distance of the vessel that avoid, for example, the heat of the sensors with the vessels, and of course to cause any damage with the equipment, okay? So here we have different ships. Of course, today we have many different kinds of sensors, like the picture that you have in the left low side of this screen. Now you can put any sensors on the below the vessel that can use acoustics, for example, to give profile of velocity of the currents and many other variables, okay? I'm going to talk about these sensors today. Of course, these vessels must have reasonable stability in order to can acquire the data with consistency, okay? And of course, satellite positioning system. Of course, every ship, bigger or small today, need to have satellite positioning systems. It's very important. But for us, because as you're going to see during the class of today, before you go to the sea with your vessel, you need to plan your mission. You need to, in order to understand the phenomenon that you want to describe, you need to plan how you're going to acquire this data with your ship. So you're must plan the route of the ship, and then you mark exact points that you need to acquire data. And so satellite positioning system is very important in order for you to acquire the data in the position that you planned originally before to go to the sea. So the first equipment, and then one of the oldest oceanographic instruments that we have, is the Nansen bottle. Nansen bottle was developed by a professional oceanographer called Nansen. He was European. I don't know if he was Norwegian. I think so. And Nansen was very important also because he's one of the researchers that started to observe the influence of the rotation in the deflection of the ocean currents that were forced by winds, okay? He came before Ekman, that after him got to develop a theory to quantify this effect. But Nansen was the first one that see this influence of the deflection of the ocean currents caused by the rotation, the effect of the Earth's rotation. But the Nansen bottle, as I said, is one of the oldest oceanographic instruments, and is used to collect water at a certain depth. It's a bottle, okay? As you see in this picture on the left side, is a bottle that you put in a cable, okay? And then you can put, how can I say, weight in the cable, and then you launch the weights. He hits at the bottle, and the bottle, as the draw are showing to you, just drive, okay, in the opposite direction, and then open and then the bottle became full of water, acquired the water, okay? And then you can take again the bottle to the ship and analyze the water sample, like, for example, go to a laboratory or put in any sensor to see the salinity concentration. And you have, together with the bottle, some thermometers. So, as I said, to use one of the oldest oceanographic instruments. So you have analogical thermometers. When the bottle do this movement, so abrupt movement, the thermometer just, I don't know how to say this word in English, but like a strangulate, no, I don't know how to say it. The bubble of the thermometer just broke, and it was marked the temperature. So, of course, the cable is, you can mark the meters in the cable, so you know exactly the depth that you're gonna just open the bottle. And then you take this information again to the ship and can acquire, for example, data of temperature, salinity, and other chemical variables that could be analyzed by the water sample, okay? So many things in oceanography, mainly in the first half of the last century, was acquired and was described using this kind of instrument, okay? And then you have the, how can I say, the more modern Nansen bottle that is called Niskin bottle. So the Niskin bottle don't do that movement of the Nansen bottle. It just goes in the vertical position and just go to the depth that you want to collect your data and open. And then became full of water, and then you can just take again the bottle to your ship and analyze the water sample, okay? This is the Niskin bottles. And then you can, of course, take the water sample for a range of measurements, including pigments, nutrients, plankton, salinity. And of course, you can have a thermometer also to acquire temperature information. So what you can do, oceanographers does a lot in your oceanographic commissions, is use a set of Niskin bottles that you can call rosettes, okay? So in the photo that you are seeing in the right side of the screen is a rosette station sampler operation. So as you see, you have for about 14 or 12 rosette stations, Niskin bottles, okay, that you can open the bottles in different depths in order to acquire samples of the water in different depths to study many different oceanographic variables. You're going to see that the rosette station sampler, most of the time is used together with another sensor that we're going to talk further. There is the CTD, the conductive temperature depth sensor, that acquires data in a digital way, and it is an electrical sensor that's of temperature and salinity, okay? But I will show to you why rosette is most of the time used together with this sensor. But now it's important for you only to know that you can acquire water samples in different depths in order to have information about many different oceanographic variables, such as, for us, directly associated with physical oceanography, the salinity concentration. So the other instrument that is very important also and is very used still today in oceanography is the XBT, or the batch thermograph. Is equipment used to obtain vertical temperature profiles. Yeah? It's also called XBT. It's a disposable projector with a temperature sensor, a thermistor, attached, and a very thin line attached to a launch unit. They have a sinker on the front and can be launched from the vessel while in motion. The operation is like you see in the photo. So a person goes there with a kind of a pistol, where this mini torpedo, I don't know what to say in English, is like a torpedo, and then you can put it inside this pistol, and it has a very thin cable where it transmits the data. It's you lost the equipment after the operation, okay? It's not very sustainable. And then you just throw it over the ship, and it produces this kind of profiles, of vertical profiles of temperature that you are seeing in the right side of the screen, okay? So it's very important, this equipment. As I said to you, is still very used around the world. I think that NOAA, the National Ocean Atmosphere Administration of the United States, has a lot of monitored sections, ocean sections around the world that still uses this kind of equipment to have continuous monitoring of temperature profiles. So this is an example. This is the line AX97 XBT of XBT that you have here along the coast of Brazil, between the coast of Rio de Janeiro and the island of Trindade. So this red line that you are seeing on the left side is the points where opportunity vessels passes and launches XBTs. And after this launch of XBT, it's possible to produce sections that you see in the low middle position of our screen with the section of temperature of the water column, okay? So to get with these sections of temperature, for example, is possible, for example, to estimate the pressure gradients inside the water columns. And if, as you know, the latitude where you are, you can apply the dynamic method that I showed to you in my class of the day before yesterday, in order to acquire the geostrophic velocity. So you have an idea of the volume transport and the transport of the currents that passes through this section. In this case, I'm talking about the Brazil current. That is a very important current that passes along our coast here in the southeast region of Brazil. So this kind of measurements are done for about 15, 16 years. So it's very nice because now you can see not only seasonal variations, but interannual variations that occur in the Brazil current in this section. So, okay, it's very nice to understand many different scales of time, the transfer of volume associated with Brazil currents. You can launch also XBT from airplanes. So they call AXBT. So you can launch for airplanes, and then you can have a very big area in the oceans with temperature profiles in order to do your studies. As I said to you, it's not too very sustainable because you lost your equipment, the sensor, the thermistor stays in the bottom of the ocean, okay, but it's still very used in the oceanography. So this is the CTD, the conductivity temperature depth, okay? It's an electronic instrument that measures vertical profiles of temperature and salinity with depth. Of course, you can have other sensors to measure, for example, dissolved oxygen, pH, and other parameters. So this is a photo of the CTD. You have in different size now to use in coastal regions, very shallow regions. You have CTD that's maybe it's 10 or 15 centimeters, very small, but the ones that we are using at the oceans are bigger, okay? And then you have basically a big cylinder where the electronics are that will measure the temperature and the salinity by using the conductivity, of course. And you have a pump, of course, to pump some samples of water inside the cylinders in order to acquire basically the salinity concentration and the others properties. You have the sensors now, pH and dissolved oxygen, and then you can do the same that can do the thing that I'm talking to you some slides ago. Okay, you can use the CTD together with a Rosette sample, and why you use that? To calibrate the electronic sensors that CTD has. Okay, CTD is very nice, very useful, very practical, but electronics sometimes fails. So you need to monitor in some periods the acquisitions of data in order to have, if you need to remove the CTD, recalibrate the sensor and throw it again in the water, okay? And this, how can I say this word in English? You have a structure around the CTD, okay, as a kind of a jail, because to protect the CTD not to impact and hit the vessel. And if it hits, it is protected by this structure around, okay? So this is, Livia, can you say a little bit more? I think that this was a commission that Livia participated here in South Atlantic Basin.
Yeah, I forgot to tell you that I put some more pictures about
Okay, nice.
The Rosette
Very beautiful.
CTD. Yeah, these are in detail all the bottles and how we kind of get them ready. Just attach them to this. You have something here that traps it,
Yes,
and then it goes
the sensor that just
Yeah,
leave the,
goes down. Yeah, and then we send kind of a weight to release those pins. We call it, I think, messenger. Yeah.
messenger.
And
That's
you
it.
you can see when it's all wired up to the ship, you can see in real time the temperature that it's measuring, the conductivity, the depth. So when you, because you know the depth in real time, you can say, now I want to close that the bottle number 3 now, so it sends the messenger of bottle number three in the depth that you want. So when it comes back, you know exactly which depths you have samples on your bottles. That's it.
And no, stay here. You have the video.
Yeah, but you can pass it.
Okay,
No,
only to talk a little bit about what Livia said. We call the temperature and salinity are conservative properties, and these conservative properties, as I mentioned for you in the first class, the temperature and the salinity are very important to define the water masses, okay? But you can use what you call non-conservative properties like dissolved oxygen also to classify some water masses that we found in the ocean. So that's why it's important to also not only you can use, of course, this in operation to calibrate the CTD, but it's also important because can acquire a water sample that can analyze different oceanographic variables like dissolved oxygen, trying to understand and classify better other properties that are associated with some water masses, okay? And this is very important also for many different students in oceanography, not only physical oceanography, but in biological oceanography and chemical oceanography, okay? And let's go.
Yeah, just one more thing. I don't know if Luis Paulo probably did that also to prepare CTD Rosette.
No, I
Just-
didn't prepare.
No,
I just participated in the commission that that's launched.
you're gonna see a little video that we are preparing it. So just to let you know, this thing here that we are trapping the top of the bottle to the pin. This bottle is very these mechanisms here are very strong. Okay, so because it can, when the bottle shuts down, it can be loose, you know, so you have to really use your strength to pin those ropes and keep them open. Otherwise they would on the way up they would like mix other layers of water along within the bottle, and we don't want that. So it's really hard to make this preparation. Is really tough. So just this
is the video.
Now the video is this.
Okay.
So this is us preparing.
Oh.
This is on top of the ship. Yeah. See, this is me. So I'm really using my all of me because it's tall. It's a tall structure, and you have to go all the way to the center. This is Laís. Coincidentally, we did this cruise together. It was a cruise from, it left South Africa, and we crossed the Atlantic towards Rio here.
Ah, nice, nice.
So it was a very, I think Lais agrees with me, it was a very enriching opportunity, and we learned a lot. And this is now how it's launched.
Launch the CTD is in horizontal position.
Yeah, it's right here.
Yeah.
So all the bottles are prepared.
Okay. Very, very beautiful. The blue of the ocean in
Yeah.
deep regions.
It's almost purple, right?
It's almost purple.
It's very beautiful. So that's it.
Very nice. So let's go. Opa. Yes. So now how CTG is used on traditional oceanographic commissions, okay? And after further in my presentation, you understand why I'm calling traditional oceanographic commissions. So in the left side of the screen, you are seeing a picture, a map with the coast of Brazil here near our states, the state of Rio de Janeiro, in the southeast region of Brazil. And these yellow points that you are seeing over the black area of the map, that is the ocean, okay, are oceanographic stations. A set of oceanographic stations compose what I call an oceanographic commissions. Of course, an oceanographic commission has a different oceanographic commission has different goals, okay? In this kind of commission, this commission that I'm showing to you, we have the goal to comprehend, okay, the salinity and temperature distribution associated with the water masses that are present in these areas, okay? So in each yellow point that we're seeing on the left side, we just go to a vessel, oceanographic vessel, stop there, okay, and launch a CTD in order to acquire the vertical profiles of temperature and salinity, okay? So in each yellow point, you have a profile of temperature and salinity. And after that, we are able to produce maps like the one that you are seeing the right side of this screen, okay? Of course, after to produce this map, you can analyze the data that you acquire in your commission, all of the data of temperature and salinity, put them in a TS diagram, a temperature salinity diagram, see if you have any noise in some data, you can see easily. Remember that one of the demands, one of the goals to use the temperature and salinity diagram is to find and identify data that are not were not measured in a consistent way. So after this, all of this processing, we can use this data to produce maps like the one that you are seeing the right side. So, for example, here you are seeing red colors, the higher temperatures of level 5 meters, okay? And the colder colors, and the blue, green, and yellow colors are the lower values of temperature. This is very common to see. You can see near the coast of. And I use my mouse. Here, where I has, I'm going with my mouse in the northeast region of the state of Rio de Janeiro. You have all of this region with temperatures colder than the temperatures around, because here you have a very strong coastal upwelling system, okay? Remember that coastal upwelling is that phenomenon where very cold waters from the bottom of the ocean just upwells and sometimes reach the ocean surface, okay? This is happening in this region of Cabo Frio. It's very common. And around you see higher temperatures that are mostly of them are associated with the transport of the Brazil current. That is a current that flows from low latitudes to high latitudes along the Brazilian coast, along this part of the Brazilian coast. And so it's common and it's normal to find warm waters associated with this flow, okay? And this kind of phenomenon is possible to be described with a traditional oceanographic commission that I'm showing to you on the left side, okay? You can also use this data to have another perspective of the data that you acquire. You can use the profiles to produce vertical sections like this one that you are seeing the left side here, okay? And this is very nice because you can see, for example, this very cold water just reaching depths associated with the continental shelf, okay? Continental shelf is this layer here where the depths are still shallow compared with the deep ocean, okay? After that, you have a very high slope here that's alluvial and going to abyssal regions. But you can see, for example, near here, in the southern part of my oceanographic commission, you can see that this cold water sometimes could reach the continental shelf, okay? And if you go to another position, now in section 2, very near the place that I told you, Cabo Frio, the city of Cabo Frio, where you have that coastal upwelling system, you can see even this cold water going to the sea surface, okay? And why this happens? This happens because the upwelling system that I'm told you about, okay? So this kind of oceanographic commission can produce data that is very important for us oceanographers to study phenomena like this, okay? That I'm showing to you. And let's go. So I'm talking about temperature, salinity, variables, and how they are mostly of the time acquired by sensors. I have a question.
Yes.
Can you?
Yes, Louis, can
yeah.
you hear me?
Yes, I can hear you.
Great. Sorry for interrupting. It's just a very random question, but I was wondering, while gathering all this data, I was just wondering if there is also like traditional knowledge data sometimes collected, because I can imagine in upwelling systems, like over the centuries, maybe there was a change in, like fish that you could fish there if the upwelling system is disrupted. I wonder if there's also an effort to collect those kinds of data, and if they also influence, like how those systems are mapped over the course of 50 years, for example, or stuff like that.
Very good question. You know that the upwelling coastal system of Cabo Frio, I think, is one of the most studied oceanographic phenomena in Brazil, because everything related to the oceanography started here in the southeast and south region of Brazil, here in Brazil, of course. And Cabo Frio upwelling was very studied in different aspects. In fact, you have a very important research institute that was coordinated by the Brazilian Navy in a city called Arraial do Cabo, just near Cabo Frio, and that have not only physical oceanographic area, but studies in biological oceanography, chemical oceanography, geological oceanographic area. And yes, you have different studies about the seasonality of the upwelling system in Cabo Frio, about the impact in fishery in that area is very important, because in this case, the coastal upwelling of Cabo Frio, really you have some rivers just near that region. So the rivers just put some sediments and organic matter over the ocean that goes to the bottom, the bottom of the ocean, and where the lights didn't arrive. So this organic matter stays there. And when you have the upwelling, you have vertical ascendant currents that just take this organic matter and goes to this, puts this organic matter to the sea surface, and then comes the lights, and then start the primary production. You have the bloom of algae, and together with the bloom of algae, it came all of the trophic pyramid. I don't know if I said the word in English, but if you understood, you enrich in organic matter that area, and this has a very positive impact in fishery in that area. In fact, the northeast region of Brazil, northeast region of state of Rio de Janeiro, is one that you have most part of the production of fish
in our states. So it's a very important system. And yes, you have study of many different areas of oceanography related with upwelling. And you told me about the changes in 50 years. I don't know. Yes, we have a lot of data, and maybe I cannot say properly if you have enough data to analyze in the very consistent way the impact of the phenomenon, how, for example, the climate change in the last 50 years is impacting this phenomenon, okay? But today, as you learned yesterday with Livia, and you're going to see along the course, you have this hydrodynamic basis, okay? When I said hydrodynamic basis, I'm talking about not only currents, but temperature and salinity produced by physical climate numerical models. So climate models, you don't have only atmosphere, you have a ocean, and you have all of the other components of the climate system associated. So you can have data that you can use to evaluate, for example, in a hindcast run that Livia explained for you yesterday, a run for the past, you can evaluate how the upwelling coastal system of Cabo Frio has been changed along the last 50 years. It's possible to do this kind of study. I don't know even if this study, it was already done here, okay? But it's possible to do this not only to Cabo Frio, but for any region around the world. Of course, some cares must be taken. For example, when you're looking to a process near the coast, you need to have a high resolution, okay? High space resolution. And most of the times, the global models don't have a high resolution near the coast. But you can use this information as boundary and initial conditions to regional oceanographic models, regional atmospheric models. And these models will produce this kind of information that you want in high space and time resolution. So I don't know if I respond you.
Yes, you responded me well. It's super interesting. Thank you for elaborating. You know, for example, in Europe, it's also interesting to see because we have a lot of, for example, anecdotal evidence. Many fish stocks have collapsed because of human pressure and climate change and like just different conditions. And it's just interesting because I think some things like this are anecdotal. And if those studies can also influence how you do, for example, a hindcast and how you model how initial conditions were and like how they might develop in terms of recovery or further decline in the future. That's super interesting. And yeah, also very interesting for that specific region in the coast of Brazil. Thank you.
No, you're welcome. You want to say something?
Yeah, just an additional comment. You comment about fish stocks collapsing because of climate change. Remember yesterday or the day before? I don't recall right now. Not necessarily El Niño, but that species have optimized range of temperature to live in. So I don't know if you have heard of coral bleaching. That the thing that because of high temperature and higher acidity in the ocean, the corals are dying.
Becoming white.
They're becoming white. That's why it's called coral bleaching. And corals environments are very enrichment to fish stocks because it's usually nurseries. It's usually where fish go to feed themselves. So imagine if you kill all of the base of the food web, then everything else is going to be impacted as well. And it goes into the economy because fish stocks are going to be going to diminish, right? Yeah. So you impact economy and you impact exportations, importations, and it's not about only about the environment. It's climate change is something that encompass all of us and all of in every aspect of our lives, including health. You know, if fish are not as healthy as they were, we are gonna consume them. The same thing with agriculture and livestock. So it's a really concerning matter, and in my opinion, it's usually not treated for by everyone as a concerning matter. In my opinion, the environment and climate change should be the base of everything else. The health is gonna would have to be built on top of it, also economy and all stuff like that. Just a
I like
small
that.
opinion.
I like it a lot, this team, and I think that you can summarize all of the things that Liv are saying in a word called sustainability.
Yes.
Sustainability is structured in three main pillars: economic, social, and environment. So all of these things are integrated, and this was the base to produce our 17 Sustainable Development Goals from United Nations. I'm certain that everyone know about it. And now you are in the decade of the oceans. So
Yes.
you have especially a demand of the United Nations related with the oceans that says all of the things that you said.
Yeah.
And it's important for us that deals with oceanography and the study of the oceans and ocean sciences to take care of these things.
Yeah, and think about them and share our knowledge and speak up, because eventually I think they will hear us. So that's just a small comment.
They need to. They need to.
Yeah.
So let's gonna talk a little bit about the measure of currents, the measure of the velocity field in the ocean. So basically use the current meters, okay? Current meters, as the name said, is an instrument used to measure the intensity, I mean the velocity and the direction of the sea currents. And the most, how can I say, the oldest ones, okay, the older ones, is like this. You have a rotor. I don't know if this is a word in English. I hope that you understood, okay? But I think that this gyres and measures the velocity of the currents. As the flow of the water passes through the equipment, more faster they measure, more velocities it has, and it measures. And there is how can I say it, Lenny? I don't know how to say this word in English, but you have this part of the equipment, okay, that measures the direction of the current. So here you see better, okay? Here is inside the water column, and here is out of the water, okay? So you can see better that here is you measure the velocity, and here you measure the direction. This is the older current meters. It is still used, okay, in oceanography, but now, and then you can use, I will talk about the other model, the modern model of current meters. But how you can use this current meters? You can use in structures like this one that I'm showing in the right side of the screen. You can put different current meters in different depths of water column, because you know that, as I show for you, that you have a vertical profile of velocity, of the current velocity in the water column, okay? So you need to measure velocity in different depths in order to understand well the space and time distribution of the water velocity in the place that you want to study. And most of the time, these velocities are acquired together with meteorological data in a meteorological buoy that you have over the sea surface, okay? And the other model that I told you that is very used today in oceanography is the acoustic current meter. So they use another kind of technology that by the Doppler effects, using the sound and the concentration of sediments that passes through the water column, it got to measures locally by acoustic the velocity and the direction of currents. This equipment is very used today. I will show another kind of equipment that uses the same technology, that it's possible to measure, including the vertical profile of the velocity also, okay? And the other thing that I like to stress with you is that's very important to have also, whenever it's possible, of course, to have measures of meteorological data together with oceanographic data. And you imagine why it's important. As I told you in the first class,
And one of the things that is very important to produce movement in the ocean is the winds that blows and flows over the sea surface. Okay, let's go. The other equipment that is used a lot in oceanography today is the acoustic doublet current profiling, or ADCP. Okay, it's a device that uses sound waves to measure the speed and direction of currents throughout the water column, and it's used in this way that you are seeing here in the right side of the screen. The size is for about this model that I'm showing to you. It changes the size of the model because according to the frequency that the equipment works. For example, we have equipment that has low frequencies to reach very big depths, larger depths in the water column. You can measure the vertical profile in 700, 1,000 meters depth, okay? And the other ones have more frequency to acquire in shallow areas, okay? And you can use like this. You can put one sensor at this one in the bottom and just range in all the water column, or you can put in the pier, for example, in a port, trying to measure the velocity in a section, okay? Or you can even use in a small boat, okay? And you can put here in the small boats, for example, in the side. I put the rectangle in the wrong way place. And then you can produce sections of velocity and direction as this one that you are seeing here, okay? So you can see in the red colors are the velocities that are higher, and the green and blue ones are the velocities that are lower, okay? And this is the direction of the flow. In this case, maybe it is a river, okay? So river without an influence of tide, so you have always the flow for the same direction, okay? But you can use the DCP in this way also to measure, for example, the flowing bays. So you can pass, for example, in a section, in a situation where you have high tides, and then you measure the flow for one direction, then one intensity, and then you can pass in other period where you have low tide, and then the flow will have a different direction and a different intensity. And this is important to understand many things in oceanography, in the different areas of oceanography. The other way that is the ADCP is used a lot in oceanography is like this. You can put a buoy in the surface, a meteorological with many different meteorological sensors, and then you put below the buoy, attached to the buoy, the ADCP, and then it can measure vertical or profiles, it can acquire time series plots of velocity intensity in different levels of the water column. Okay, so it's a very nice use. We have two of these types of buoy here outside the Guanabara Bay. That's just near us here in this room. And it is nice because when you have a structure like that, you can also have an antenna that gives you in real time the measures that you are acquiring. So you're not going to have only data that you need to go to the sea and took out the equipment, plug a hard drive to take the data and analyze only after, okay? You can have an antenna that produces this information in real time. So you can use this data really to monitor the present conditions of the ocean in the region that you are acquiring the data. So this is very useful, for example, for regions where you have ports or where you want to monitor different aspects of the ocean to use. For example, in the equatorial Pacific, you have an array for about 75 buoys like that. Many years ago, you have this array to monitor the oceanographic and meteorological conditions around the equatorial Pacific to study, trying to forecast and to comprehend the El Niño. Yeah? And this is projects conducted with NOAA in fact, with a laboratory that is associated with NO, the PML, the Pacific Marine Environmental Laboratory, and an agency of Japan that deals with environment also too. And this already exists for many years in that region. Maybe if you don't know, I can send you the links, because it's very nice place to see and to monitor and to comprehend if you are going to a El Niño condition, or if you are going to La Niña condition. You have also the products that comes from climate models also too, but you have the data that is acquired by these 75 met ocean buoy or meteorological oceanographic buoys. That's how we call this kind of buoy in oceanography also too, okay? And this is the problems that you have, working with oceanographic observations. You need a lot of efforts in operation and maintenance, okay? As you see, this is the ADCP before going to the water. This is the ADCP after 4 months. I don't know where this photo was acquired, but I can say you with property that this happens all of the time. Mainly in coastal regions where you have a lot of life, a lot of organic matters, you have a lot of what you call biofouling, okay? This is a DCP that you have here installed in Guanabara Bay. It wasn't too bad, okay? But of course, when the equipment starts to stay in this way that you are seeing here in this photo, the measures start to be not consistent, okay? And so it's important to go there again at the place, remove the equipment, clean the equipment, and then after that, recalibrate, and then goes again to the ocean to measure. This is another structure that you use together with a DCP, this kind of triangle, this metal triangle here at the bottom, because sometimes you have fishery activities in the area, and they just passes a net to take the fishes that is in contact with the bottom of the sea. And sometimes together with the fish, they fish your equipment. So this kind of structure doesn't, how can I say, try to avoid this kind of impact of fishing nets. And the other problem that you have, mainly with the buoys, and this is not only here in Brazil, but in many parts of the world, you have vandalism, a lot of vandalism. And so I don't know why people just see a buoy and like to take the photo, the cells, the solar photovoltaic cells and other equipment. I don't know even if why they take this and if they use it, I don't know, but take also the meteorological equipment. And this is a very huge challenge that in most of the parts of the planet, oceanographers must deal with, okay? And this is important to told you also, not only with big ships, oceanography could be conducted, okay? You can use also small ships. This small ship, this photo is from, I think, some year around 1998 and 2000, the year 2000, when I was conducting my master's degree in the Oceanographic Institute of University of São Paulo. And there they have a base, oceanographic base, research base in the south part of the littoral of the state of São Paulo that is called Cananéia. It's a very beautiful place. We have a lot of mangroves and estuaries. And this was a class of dynamics and cinematics of estuaries, is a discipline that we had in that occasion. And then you have this small, is a ship vessel, is a fish vessel that was adapted to be oceanographic vessel.
Please.
Yes.
Just a moment, because we have some questions about ADCP.
Okay.
So Lais asked, do you think ADCP equipments are more precise than current meter or mooring?
Today, I can say to you that is so is the same precision, okay? We just in the few years ago, few years, I think that was in 2020. During the pandemics, we had a big project here for us in Brazil that I will tell about this project. Was the development of an ocean observation system to Santos Basin. Santos Basin is an ocean basin inside near the southeast region of Brazil, and we had a comparative analysis between ADCP, data from ADCP, data from acoustic current meters that was acquired, and the results were very good, very well. So yes, they have quite the same precision, and you don't will compromise any information if you use HCP or current meters. They are comparable very well.
Okay, we have another one from Olga.
Yes.
Out of curiosity, how long does the ADCP live without the maintenance?
Good question. Good question. Good question. Difficult to respond, but I will try to. Okay. Well, the first thing to know is because you need to know about the battery also too. Of course, you have some batteries associated with the sensors, and so depending on the frequency that you will acquire the data, okay, the battery will just give you 2 months, 3 months, or 6 months of life of the equipment. So this is one thing to plan before to go to the sea with the equipment, okay? How much time you want to acquire the equipment and how much battery you have to keep the equipment live, okay, on. This is one thing. The other point is I think it's more difficult to respond because it depends on the region. For example, if you are in a region near the coast where you have a lot of organic matter, a lot of life near bentonic life, especially bentonic life. I don't know if you are familiar with bentonic life. Benthos is the life that lives near the bottom, okay, of the sea, basically like that. I'm not a biological oceanographer, but it's basically like this. And then this will, of course, it will impact faster the equipment. Okay, the biofouling will be faster in these areas. For example, here in Guanabara Bay, we have a very eutrophised environment. What I mean with eutrophised, not only is a coastal environment, so we have a lot of rivers arriving with organic matter, but you have a lot of pollution also too, domestic pollutions. Okay, waste basically. So of course, this turns the things even faster, okay, because you have more biofouling in these regions. When you go to oligotrophic regions, like deep ocean regions, I think that things will be better, okay, and the life of the equipment against biofouling will be, you have more period of life of the equipment. I respond you? I don't.
And we have a following question.
Yeah.
That can one change the battery for a new one? Yes. Right.
Yes, of course. In fact, you do that with different kinds of equipment. Okay, it's still the autonomous one that I'm going to talk. Is still in this class, like the submarine vehicles. Yes, you need to change the battery, of course. But I just want to said before that it's important to understand, for example, sometimes it's a decision that depends on the money that you have, okay? For example, sometimes I need to acquire this data at least each 15 minutes, okay? But each 15 minutes, I need to buy 6 packages of battery, and I don't have the money to buy 6 packages of battery. I have money to buy only 3 packages of battery. So I need to maybe to acquire the data not in 15 minutes, but maybe in 30 minutes, and then I will give more life to the measure of my equipment, okay? It's a decision that depends of different variables, okay? In the perfect world, with a lot of resources to go with your project, you don't, doesn't matter. This will not have a problem for you because you can buy many packages of battery and change the package whenever you want, okay? But to change the package of battery, sometimes You need to have an operations. If you are in shallow region, you go with a diver, and then a diver go there, remove the equipment, go to the sea surface, then you clean the equipment, change the battery package, and throw it again in the same region. Okay.
Thank
Uh,
you
just-
very much.
Just the last one, when you were talking about those fish net
Yes.
to protect the ADCP. So we have I researched and I to know how the name of that fish nets, because I already told them it's called trolls.
Trolls. Okay.
Trolls. And then Olga asked if ADCPs get into nets when vessel trolls.
Yes, so that's why most of the times people uses people now oceanographers uses that kind of structure that I showed to you, that kind of metal structure around the ADCP. This is not only to guarantee that the ADCP will be in the vertical position at the bottom, it's also to protect against nets. And I don't know, this is not good to say for the fishers, but most of the times when the nets passes over there, sometimes it I don't know how to say it cuts the nets. Okay, of course that here in Brazil, and I think that most parts of the world, when you put a fixed equipment in the ocean, you need to talk with the Navy, and Navy produces a advertisement, announce for all the community of fishers in the radio, talk, oh, in this region, in this latitude, in longitude, you have an equipment there, so take care. Okay, it's here in Brazil, we call it in Portuguese, aviso aos navegantes, is a shipper's advice, like that, like this. That is done by the official institution that has this responsibility, and here in Brazil is the Navy. Okay, I don't know if I respond you.
Yeah, you did. Thank you very much. And also, trawling is a super damaging practice for the ecosystem. So if the nets get torn, then, no one's crying. Thank you.
Okay. Yes, I know that also too. Yeah.
Can I plug your computer to the battery?
To the back. Yes.
Yeah,
Okay.
it's-
See. Yeah. Have some apart. So let's go. This is below. It's me, 25 years younger than now. Okay. And this is to talk about other sensors that we have that you use mainly in coastal region. That is what you call multi-parametric platforms. Okay, why is multi-parametric platform? Because this is small sensor, you can measure current, velocity, temperature, salinity, pH, turbidity, dissolved oxygen, and many other physical chemical properties that is important to use in oceanographic shallow water studies, okay? And in this case, I was working in an estuary that has for about 10 meters depth, so it's very shallow. And this blue cable that you are seeing going out of this yellow structure here, okay, goes directly to the equipment, as you see the blue cable here. So it has, I don't know, maybe 20 meters of cable. And as you just launch the equipment at the seawater and take the notes of the values here that was in this screen, okay? And after that, we have, after 20 hours of acquisition of data, we have enough data, for example, to study the mixture, the process of mixtures, and the stratification that you have in this estuary. Yeah, as I said to you, it's very important to study the tides at the estuary, and the balance between the river discharge. So the current meter was very important to help us in acquire this information, to classify this estuary, and also the temperature and salinity, mainly the salinity, to understand how is the intensity of the mixture processes in this estuary, okay? And this is a kind of a multi-parameter platform. It's very small. This is big that I'm just launching here because we have the current meter, but sometimes when you don't have the current meter, it's for about 30 centimeters or less, okay? And this is the remote, the satellites, okay? Satellites was a tool. This slide is a little old because now I'm seeing, I wrote that it's a tool with great potential. It's already has a great potential in oceanographic studies. It's a very powerful tool now. So it can cover a large oceanic region and monitor the spatial and temporal variability of different oceanographic phenomena in real time. That's why it's so important. We had a planet of more than 70% covered by the oceans. We are not able to put each kilometer of the ocean one oceanographic buoy, for example. Of course, is not viable to do that because of the price, because of the logistics, because of many aspects. And so satellite gave to us the opportunity to evaluate this oceanographic process, not only in a point, but in an area. Of course, there are many scientific efforts related with the measures of oceanographic parameters using satellites. It's not so easy, but today they give to us sea surface temperature, sea surface salinity, sea surface height, sea surface wind, chlorophyll concentration, underwater relief, and in indirect way, you can have other parameters that are very important for us. I will show to you not only today, but in our last class, in a direct application of data acquired from remote sensing in R&D projects, research and development projects, okay? So basically, you have two different kinds of sensors in the satellites. The radar satellites, you have the optical sensors, and you have the radar, the sensors, okay? And this acronym here, SAR, is synthetic aperture radar, okay? It's a sensor that are inside or attached of the satellite and can measure images, this gray image that you are seeing here. And then with this gray image, you can process this image and have, for example, the wind field over a big area over the ocean, okay? So today, for example, here in Brazil, we have a lot of studies that are using this kind of information to study the wind, the sea surface wind energy potential here in Brazil, okay? Offshore wind energy potential here in Brazil, dealing directly with the energy transition, okay, that you are thinking here. You can also use this gray image to process and to acquire information about oil spills over the sea surface. I will show you on the last class some project that we have the opportunity to conduct here in Brazil that uses this technology to do both things, acquire wind field and identify oil spills over the ocean, okay, using this kind of sensors. That is very nice because the capability of use these images doesn't matter if it's day or night, okay? It can measure all of the things and is very used today. The optical satellites produces to us, for example, the color of the ocean, the sea surface temperature, the sea surface salinity, the sea surface height. All of these things came from the optical satellites, okay? Let's go to some, this is the area evaluation. This is very important to mention. So let me show to you some of the products that could be produced by satellites, okay? So talking about the optical sensor, the chlorophyll surface field. So this is the coast of, the west coast of South America. So we have here Chile, and here you have Peru countries, okay? And the red colors indicates a high primary production area near the coast, okay? This is very common in this area and also in the west coast of Africa, okay? Because of that systems of upwelling that we have around the eastern parts of the ocean bases because of the sense of movement of the Earth's rotation, okay? So all of these areas are more probable to have upwelling systems. And in these both regions, these upwelling systems enrich a lot the area of nutrients and produces a high fishery areas, okay? So this is very important. El Nino study, for example, the name of El Nino came because of the impact of the El Nino that El Nino produces in the 50s of last century, okay? In the fishery of the anchoveta, the Peruvian anchoveta is a species of fish that were at that occasion very important for the economy of Peru. And during El Nino, that happened at the end of the year, near the Christmas. That's why it's El Nino. El Nino is a mention of the Jesus boy, okay? And El Nino comes and avoids these processes of coastal upwelling, okay? In fact, you have warmer waters when you have El Nino in these areas, and you avoid the upwelling, and the fishery just go down, okay? And this, at that occasion, caused a very huge impact in the Peru economy. So, and of course, primary production also give to us a lot of information também, also, to understand different oceanographic processes. You can understand, for example, you can see some meanders and sometimes some eddies associated with a higher primary production and lower primary production in some areas. And this is the surface temperature field, okay? You see a lot these maps I'm certainly about. And that's it. I'm talking, this is the spectrum, okay, of radiation that comes to the Earth. So we have the visible, we have the infrared. The infrared is associated with this kind of data and this kind of data. The sea surface temperature field and the chlorophyll are associated with the infrared frequency. The visible one is associated with the image that we have with high resolution from cities and any other place that you have acquired by satellites. And we're going to talk on some slides further about the radial resolution. That is the resolution of the synthetic aperture radar that I'm told you about, okay? But let's still talk about the products that we can acquire with optical sensors, okay? Yes.
We have a question. How do we choose the measured parameters of optical sensors? How do we choose those parameters?
Oh, no. You mean you choose the parameters to acquire the image? That's it?
No, it's why we are measuring them, because it's the satellites that they are measuring, but I don't know how we are going to know that which parameter is.
No. In practice, you have some sites, some places to go, for example, and then you have, for example, you have a project called Aviso, AVISO, where you can acquire, for example, directly from satellites, always already processed for you, the fields of sea surface temperature, sea surface salinity, sea surface rate, that is this field that I'm showing the screen now. I don't know, that's it that you asked it? I think I don't understand very well.
So it's okay. So we have a site that
yes. All of these things. No, you don't have to. I only showed to you a little bit about the technology, about the radar frequency, but you don't need to do that. Okay. In fact, you have different levels of processes. Okay. You have, for example, more raw data. Now, for people that deal directly with this area of research that call it remote sensing. Okay, sometimes it's important for them to work with the raw data, the less processed data, okay, to work with that data and produce more specific products. But you have, I think that's L4, L3, L2. L4 is the most processed data, so you can take the data ready for you to use in your analysis, to use in your model as a boundary condition or as an initial condition, for example, okay? And this is ready for you, ready for the community, okay? You can be blind about the technical aspects related with the satellites. But it's good not to be so blind, okay? It's good to know a little bit about the technology, to know the limitations that you have. For example, now talking a little bit about the limitations, sometimes this kind of data near coastal areas, you must take some care to use it, because you can have some noise related with the continental influence, okay? But this is more specific aspects that I'm only saying to you. If you decide to go more deeply in the remote sensing area, evidently you will study these kinds of impacts. But you don't need to care at this moment. All of the data that you access, even the data that is near the coast, it was already processed by these huge centers of research like NOAA, like Copernicus, okay? They produce this data in a very high quality for us. So let's go. The other kind of equipment that we have in satellites is the scatterometer. Scatterometer is a kind of radar that you can emit a pulse, a signal. The signal goes to the sea surface and again comes back, have a backscatter effect. It comes back to the satellite, to the sensor that is in satellite, and produces, for example, the sea surface wind field directly. Okay, and this is, you see this map here where I'm with my course. My cursor, here you have some black areas. These black areas is because you have the passages of the satellites. And then sometimes you have some shadow zones, areas where the data was not acquired. But of course, most of the times, the research institutes do the following. They just take image passages from different times and just process these images, interpolate basically these images to have the full picture. Okay, cover the full picture of the whole ocean covered by data. And this you have these arrows. The arrows mark the direction of the wind, and the colors the intensity of the winds that is acquired by this sensor called scatterometer. Okay, sea surface salinity is more recently that was acquired by satellites because it's not directly acquired. Okay, you need to do some indirect measurements to acquire sea surface salinity, but you can acquire today sea surface salinity. It's very nice. You can see here the north coast of Brazil, an area with very low salinity, blue up here, probably is related with the waters that was drained by the Amazon River. Okay, here, and it's very important for this region. And you can see here in the Mediterranean a region with a lot of red here. Okay, and red is high salinity, and you know that you have here inside Mediterranean a region with a very high salinity. And below here, we have another variable, oceanographic variable, that is very important for us, the sea surface height. The sea surface height, I'm talking about the sea surface height in relation with the mean level of the ocean, okay? So the sea surface height, there is showed here in the three-dimensional, or trying to be showed in a three-dimensional way, is nice for you to understand, because this sea surface height distribution in space will help us to measure the pressure gradient force between different places of the ocean. And with the pressure gradient force, we can use the geostrophic balance relation to estimate the geostrophic velocity. So you can use this sea surface height to have an important information about the dynamic of the ocean. That's why one of the nicknames of the sea surface height for physical oceanographers mainly is dynamic topography of the ocean. Okay, dynamic because it's not a topography that is static; it's always in movement. Okay, according to the winds, according to radiation, according to any other forces that are impacting over the sea surface.
Okay, we have another question here. Is salinity measured through density in case of the scatterometer?
No, and I don't know. I'm certainly it's not with the density, okay? But I don't know the technical aspects related with the measurement of sea surface salinity. I know that is not directly acquired as the sea surface temperature. Sea surface temperature, you have the infrared sensor that takes directly the temperature of the sea surface. But the salinity, directly, I mean, it's not so direct. We have models also too, okay? The pulse, depending of the atmospheric characteristics of the area that you are launching the infrared ray, you have some mathematical formula to take the signal that you are acquiring, put in this mathematical form, and produce sea surface temperature. Sea surface salinity has the same, has the processes quite similar as this, but I know that it has more complexities. Okay, that's why I told you that is used more recently in oceanography. But I must say that I don't know the technical aspects related with the determination of the surface salinity with satellites. So I prefer not talk about.
Yeah, thank you. That's fine.
Let's go. And now let's go to another frequency, the radio frequency. That is this gray image that I told you about. Okay, this gray image is very useful for many different demands of the society that oceanographers or people that work with ocean science could attend. For example, the identification of oil spills over the ocean. Not only oil spills, okay, but when you find dark features in a radio imaging, in a radar image over the sea surface, it's an indication that could be a oil spill. Not always is an oil spill. Okay, this is important. For example, here we are near the Cabo Santo Cape. It's a northern region of Cabo Frio, where you have that strong upwelling, coastal upwelling system. Okay, here in Santo Tomé you have upwelling also too. So this gray, this black slick that you are seeing here is not an oil spill. In this region, you need to cross the information with other information, because you know that sometimes when you have cold water, the surface of the ocean stay more, how can I say, more static, okay? And so the sign that the radar on satellite receives is will produce this kind of black area here, okay, like a shadow. And this is mainly because of the upwelling system that we have here with colder temperatures. It's not an oil spill, and not an oil leak, okay? But when you analyze this one that is far from this effect here, so you can say that this is an oil leak, okay? It's not so simple as this that I'm showing, demonstrated to you. You have to cross this information with many other variables. We have some expertise here in our research group in do that. For example, you need to see, as I told you, the sea surface temperature field. You need to see if you have any meteorological effect in that area. For example, a wind that blows directly over the sea surface, or it will plane the sea surface and will cause maybe what you call a false target, not an oil leak, but any other influence, okay, of a meteorological oceanographic parameter. You need to study, for example, if you have any structure that produces oil in that region. You need to know even the geological history of the region, because sometimes you have some natural processes that the oil just naturally comes from the deep of from the bottom of the ocean to the sea surface. Okay, so there are different aspects that you need to cross the information. But what I'm trying to explain to you is that remote sensing radar images are very useful to identify oil at the ocean. And this is not only Brazil, this is in different parts of the world. Many people, even mostly of the time, the person that works in oil companies are very interested in studying these technologies to try to identify any oil spill, and of course produce the mitigation activities faster. Okay, this is the idea. And this is another application that is going to be very useful in the next years, by the means of the energy transition. That is the acquisition of the sea surface wind field to produce the wind resource energy field in a sea surface region. So this is an image of radar from satellite that could have 20 meters of space resolution. So it's much high resolution in an area that could have 100 by 100 kilometers. So it's a lot of information with very high resolution. So for you have an idea, this picture where I'm passing the mouse here is a product that's generated by using a global climatological atmospheric base called MEHA, okay? Is a global climatological model. So you see here that all of the winds is going in the same direction and with the same intensity. When I use this image to have the wind field, in the same time, look at the difference. Look how I can differ in intensity the winds from one side to one side of the picture of the area, and look at the difference that you can see in the direction of the wind field. Okay, this is possible because the image has much more resolution than the global climatological model, atmospheric model that has for about 30 kilometers of space resolution. So it's very powerful. Of course, you don't have these images in a high frequency, okay? But is very important that it's being very used by the energy companies in order to understand the wind offshore energy potential in many regions around the world, okay?
We have another questions here.
Yeah.
Is it common that oil companies also have to forecast environmental impact scenarios in case of a spill before new rigs are being built? Sorry if this was discussed before, I didn't catch it.
No, it's
And
very...
we have another person after too that raised.
Okay. Only to say, yes, of course, they are very interested in. Here in Brazil, I think that I have more space to talk about this further, but only to mention here in university, especially our group that is composed by oceanographers, as myself and Livia, meteorologists, geologists, geographers, we have a lot of R&D projects, research and development projects financed by energy companies or oil companies, okay, to study technology related with the identification of oil spill and the application of numerical models that must be applied by the means to identify, for example, if I have an oil spill, identify the oil spill, and then I must know where the oil goes, okay? And why they want to know that? Because with this information, they could plan a strategy to mitigate the oil spill, okay? Trying to go there in the fastest way, and okay, gonna try to contain the oil spill. And so, yes, we have also an environmental agency here in Brazil, IBAMA, that give the licenses for any oil company that wants to produce oil here in Brazil. So before the production of oil starts, they need to present to this agency a technical reports showing to them many different conditions of the region, of oceanographic conditions and meteorological conditions that could happen, and how an oil spill would behave in this area, okay? So with this in mind, the oil company could present also a mitigation plan, okay? This is an obligation. And the agency could analyze and see, okay, I will give you a license. Oh, no, in this region, I cannot give you a license because the probability to have a strong accident with a strong impact is very, how can I say, could occur, really could occur. So I will not give you a license. That's it, okay? But there's a lot of resource in studying in science related directly with this kind of problem.
Someone else raised their hand. Can ask them to talk.
Yeah. You said that sometimes we could mistake black spots for upwelling processes.
Sorry, your voice are a little farther. Can you
Is
repeat,
it
please?
better now? Okay. Sometimes we can mistake areas of oil spills, the black parts, with
Yes.
upwelling systems, right?
Yes.
So
Yes.
what's it's the impact of upwelling system doing to the radar? Like what's information it's giving the radar so it appears as a black spot?
Yes, it appears as a black spot, like this picture that you're seeing here. You
Yeah.
can see my cursor.
Yeah.
This is probably because of two things. Or the sea surface temperature is colder because of the upwell of cold waters, or you already has a bloom of algae. A bloom of algae also turns the sea surface plane, okay? And so the sign of the radar receive is this as a black area, as a shadow zone
Okay.
area, okay? So, and maybe the two things, okay? Because it's directly
Okay.
related. That's it.
Thank you.
Okay, you're welcome.
Can
Let's
I?
go.
Sorry,
Oh, sorry.
Liz, can I ask? Just to clarify this. So does it mean that in this kind of images, colder is darker, and then
Yeah.
warmer is lighter? Okay.
Yes. Relative temperature, of course. Yes, that's it. Only to say, okay, if you can have also atmospheric phenomena that could cause also these shadow areas, okay? But related with the sea surface temperature is like that, that you said. So what is nice that is coming, okay? You're gonna have much more new constellations of satellites. So the frequency of passage of satellites in one area will increase in the next years. And another development, the nano satellites. Look at these satellites. You can take it in one hand. So you don't need a very big rocket to launch the satellites to the space. You can use a small one, okay? So this turns the things less expensive, okay? Because an image of a radar image, for example, here in Brazil for us, if I want to, of course, we have some free images available. The Sentinel missions from Copernicus, for example, is freely available. But you have one image here in some parts of the coast of Brazil in each 12 days. So if you want to monitor in a high frequency one process, we are not be able to do that with free Sentinel images, okay? You need to buy images from other companies. And each image costs us for about $3,000 and a half dollars. Is when you want to buy one specific image for one period and one area, okay? So for us, it's expensive. But the nanosatellites are coming, and maybe it will, because the nanosatellites still don't have the technology of put a radar sensor here, okay? But there are other sensors, like the infrared ones, that are able to be here in a scale, in a spatial scale, that is smaller also too. So this guy will cause a big revolution, without doubt, in our research area. This is another kind of remote sensing. I'm talking about the satellite remote sensing. And now you have also the radars that were used by ships, by ocean vessels, for example. The same technology could be used by antennas that you can put in the continent, and they are emitting pulses, signals of pulses that goes to the sea surface and back again, the signal back, and according to the ruggedness of the ocean, the signal back again, you have a processor that transforms the signal in sea surface velocity fields in real time. This is very nice because, and I became scared sometimes because I think that one day they would not gonna need more ocean waters. No, I don't think so, because they need to forecast. But it's very nice to see the powerful of this kind of equipment. And this equipment was very used in an accident that we have in the Gulf of Mexico for some years ago. I don't know if you remember or have heard about the Deep Horizon accident, a very big platform, oil platform from BP, just had a fire, and it was oil a lot for about 1 month. It was like a hole in the bottom of the ocean with oil just coming to the ocean for about 1 month. And so this kind of technology was very used at that time to trying to understand the path of the oil spill, trying to mitigate the impact. It was very bad. But this technology is very useful today. We have, you can use, this is an antenna that was installed near the island of Cabo Frio region, the region that I talking a lot of you about the coastal operating system, very beautiful area. And then you have this antenna with this view, okay, for the ocean. This is a structure that you need, the people need to install to support with energy the antenna. And the antenna produces this kind of field here. I know there is smaller, but this is the sea surface current velocity field, okay? And they produce these fields for each 10 minutes, okay? And so what we had the opportunity to use this high frequency radar system data together with our ocean modeling application in the area. The name of this kind of antenna is an HF radar, but the name of the company was Kodar. And this is one field that they measure in the day of 25 of June 22. This is our model, ocean model results. Repair that you can see that the ocean model results, when compared with the ocean data, is quite different, okay? By the colors you can see, and by the density of the errors, you can see that it's very different. Then, what we developed in this project was a data assimilation system, a radar data assimilation system. So this is the results in our assimilation ocean model. You can see that is much different than the free model, and is quite similar with the data that was observed by the antenna. This is the power that the assimilation processes in ocean models, in atmospheric models, has, okay? To turn near, approximate the model results to the data truth, the ocean data truth, okay? So this technique that I'm going to talk a little bit deeper in the class of tomorrow. So let's go. The radar is also used in vessels, for example, to measure other kinds of oceanographic phenomena, like the wave field. So this is animation here, show the crests and related with the waves propagation. This is a ship, okay? So you have a shadow zone that the antenna of radar is not able to acquire any data. And after one shadow, this shadow zone, you can have in real time the wave data, the wave height field, and the wave direction of propagation. These are some diagrams that you can produce using this kind of technology. Britt?
Yeah, I was gonna say that.
Let's gonna say, and I don't know if I'm gonna have. Oh, let's
No,
take a break.
you can finish.
Okay.
Yeah. So I think we can have a 10-minute break now. What do you think? And we can come back here for this other part. Okay?
Real 10 minutes break. 10 minutes break.
10 minutes break. Yes.
Okay.
Okay.
Let's
See you
go.
later.
Hello. Let's gonna come back. Everyone is there off already. Livia, everyone is there.
Yeah.
So let's go. So let's gonna start about the equipment that are, in my opinion, okay, causing a revolution in oceanography. I'm talking about the low carbon emission equipment, okay? The first one is the surface drifter. What is a surface drifter? As the own name of the equipment says, is a buoy equipped with a GPS, okay, a global positional system sensor. So it has many different of surface drifters, but this one is used a lot to study ocean currents in deep, in medium to deep depth regions. Okay, what you have the buoy, okay, the body of the buoy that is integrated with GPS. As I told you, you have an antenna that transmits the data of the position of the buoy, and sometimes you have a cable with I don't know how to say this word in English. Okay, a sail. Okay, a sail. That this is the measures. Okay, it's for about 18 meters depth to take the velocity of the current, really the currents, not only the effect of the winds that act directly over the buoy, but the ocean currents that the wind is producing. Okay, so it measures the current, the velocity and direction. Of course, you could put here inside the buoy other parameters, other sensors, like the sea surface temperature and sea surface pressure. Okay, so you can launch different, many different sensors like this. Okay, I think that Liva showed a diagram of this kind of sensor, type of sensor yesterday. And after one time, you're gonna have a map like this one. Sometimes people use it to call this kind of map as a spaghetti map, because the trajectories of the buoys, of the drifters, produces a kind of a spaghetti, okay? But you can see here, again, in the southeast region of Brazil, in the south region of Brazil, that the most part of the trajectories of these buoys that were launched in an offshore region near the city of Cabo Frio, in the northern region of the state of Rio de Janeiro, came to the south. And why they came to the south? Because here, as I told you before, you have a current here called southward current, called Brazil current, that comes from the north to the south, okay, in this region, transporting warm waters, okay? That is very important for us to study for many different aspects, not only related to demands of the society and the demands of the oil companies, but also related with demands of the society. Of course, this to monitor the transport of these currents is directly related, for example, to anomalies of the sea surface temperature field that could affect the climate in these near continental areas, okay? So they are important for different aspects. And of course, if I take this rectangle here and take a zoom here, you can see that we are not able not only to reproduce the main transport of the currents, but we are also able to represent and to understand and to identify the presence of important oceanographic features related with the Brazil current movement. This is an eddy or a vortex that we have here in this region. Cabo Frio is here. Is a cyclonic movement or a clockwise movement in the southern hemisphere, okay, related with an eddy called Cabo Frio eddy, okay? It's a semi-permanent cyclonic structure that you have in this region that is very important to study, also for many different reasons. And you were able to capture the presence of this eddy
using this kind of sensors, the drifters, okay? And the drifters, of course, if you have the position in different times of the buoy, you are able to estimate the velocity, okay? The reason between the space and the time is the velocity field. So you are able to have information about the velocity. And you can see also that in this case of this sensor that I'm showing the map, you have colors, different colors in the lines, because in this sensor we have a temperature also sensor that give to us also information about the temperature field, okay? All of this information is useful for us, not only to validate ocean computational models that we apply in this region, but also we can use this information, this data, to be assimilated in our model in order to represent well the present state of the ocean. And with a better representation of the present state of the ocean, I can have better forecasters, okay? Let's go. Other, also, I think is not an autonomous, but a semi-autonomous sensor is a profiler. Profiler is a kind of a CTD, okay, that could also measure solid oxygen, turbidity, pH, and other parameters, okay? But it acts like a drifter, okay? You just launch the equipment in the ocean, okay? Here's one model of the profiler, and he starts to flow together with the currents, okay? So, but he has an antenna, so he can also transmit its position and also the data, the temperature and saline data and the other data that it acquires, okay? And the sensor has also a mechanism here that it could dives in the water column, okay? So you can, for example, give to the sensor the following instruction. For about the next 2 days, please go to the 2,000 depths, stay there for 3 days, and after that, goes again to the sea surface. Go again to the sea surface, okay? And then transmit the data for me, okay? So you don't have the control to where this sensor goes, okay? He goes together with the currents. But you have the control, you got to control the depth at which you have that want to has the position of the equipment, okay? So this kind of equipment is very nice, very easy to launch at the water, okay? This is a very small ship. You can go there and launch this. This is a little bit about the operation of launch and recovery of the equipment. You can recover the equipment. Most of the times the battery goes down, it's off, and then you lost the signal, and then you don't know where the sensor are. But until that time, the sensor transmit all of the data that they acquired for you. So you have all of this data storage, okay, transmitted by the satellite system for your antenna in continent. And you can, of course, control what you call parking depth, okay, the parking depth of the profiler. So it's very useful to acquire temperature and salinity profiles over an area covered by, for example, an important ocean current. And if you want to understand, for example, the structure of water masses that are transported or that are that exist in a ocean current system, okay? So here we have an example of the launch of all of these ponds profiler that was launched in this section here, okay? And these are the kind of profiles that it produces, okay? So you have here in blue a vertical salinity profile, in red the temperature profile until 2,000 meter depth, okay? And here you have the density profile that you can estimate, of course, using the temperature and salinity values. Using what? That's equation that I told you about the equation of state of seawater, okay? That now you know to calculate using the Python routines of Livia, that Livia just showed to you. And this is a different data sets, okay? Here you have one date, this is another date, the same equipment. You can see that changes a little bit the vertical profiles and the density distribution at the water column, okay? This is another, and now I'm talking about a really autonomous equipment, okay? This is the glider. Glider is causing a real revolution in operational oceanography and in oceanography as a whole, okay? And what is a glider? As an autonomous submarine vehicle, yeah? Like the name said, is a kind of a small submarine that you can really operate being farther for that. You can operate here a glider that is thousands of kilometers from here, okay, because it uses a satellite system, and it works like that. Yeah, you have the glider without a propeller. We have 3 gliders of this kind of model here in our laboratory, and we have glider with a propeller. I will talk more about this kind of glider, okay, but with a propeller, you have more, how can I say, adaptability of different current systems. Sometimes when you have a very huge, a very intense current system, it's not possible to use a glider like this one. You need to have a propeller to win the intensity of the current, okay? I'll show better in the next slides. And some institutions of research of oceanography in the world has really a fleet of this kind of equipment. So it's very nice because you can go to a region, okay, and you need to use one ship to cover a very big area. You can stop in one point and just launch many gliders, and each glider go to different directions, okay, to cover the whole area. And why is interesting to use gliders? First, because of the cost, okay? Maintain a vessel over the ocean is very expensive, okay? So these guys can work as a whole oceanographic vessel in different, with less expensive costs, okay? The other reason that is nice is because as soon you can have the ocean data in almost real time, okay, you can see, for example, a new oceanographic feature that occurs in one place, and oh, okay, I want to go there to investigate better that ocean feature. So you can send a message to your glider, okay, and say to him, say to him, goes to that position because I want to investigate the temperature and salinity profile in that region. And then it goes there and acquire the temperature and salinity data that you want to analyze better, okay? This is a glider operating. This orange structure that you are seeing here is the antenna of the glider. I think I don't have an image of the glider outside of the water, only inside the water. But here, okay? Here is the model that you have, the sea glider. This is the antenna, okay? Operation, this model operates from 50 to 1,000 meters depth. Horizontal displacements up to 6,000 kilometers. Can do 8 dives per day, 1 meters long. So it's easily operated by two persons. Approximately weight 52 kilograms. Collect data of temperature, salinity, solid oxygen, turbidity, chlorophyll. And the sea glider has an autonomy up to 6 months, of course, depending on the sampling frequency and the dynamics of the sampled region. Okay, and this is the simple operation carried out by 2 people, small vessel, does not require a winch. Operation lasting approximately 36 hours. This is in our case, we have a project that we need to monitor one area near the state of Rio de Janeiro, offshore region. So we go there, launch two gliders, and then come back to to the continent and wait for them do the work for us, okay? And how it works, okay? How does a glider work? Basically, a glider without propeller transforms vertical movement into horizontal movement. It becomes floatable by altering its volume. So it has, I don't know how to say in English, but it's a kind of, it's not a balloon, okay? I don't know the name in English, because it's a kind of a hydraulic balloon that just takes hydraulic oil, and when it wants to float, it just becomes bigger, okay? And the gliders goes to the surface. Anyone wants to dip, it just becomes smaller, and the weight, the volume alters, and the gliders just go deep, do the dive, okay? So that's it. The glider also has a battery, and the battery helps also in the movement from below and from down and up, okay? And the battery also do the roll movements. So you can do a curve with the glider, okay? You can really pilot the glider. And whenever it is at the sea surface, it can transmit the data that it acquires for you. And also you can send it a new mission. Now change your path, go to that place, that different place, okay? And this is a small video that I thought it was very interesting to show to you a little bit about the work of a glider. So I'll pass for you to see.
Submarine gliders make it possible to collect physiochemical data such as temperature, salinity, and oxygen levels from the sea in an autonomous and continuous way at a high spatial resolution. So SEAB has a fleet of gliders taking samples continuously in the Mediterranean Sea with the objective of obtaining data, so its characteristics may be studied and small-scale variability solved. But do you know how a glider works? The glider is ready to start the mission. The sensors and the navigation and flotation mechanisms have been checked. Inflating the bladder allows the tail to rise up and receive the operator signal. The commands which initiate the mission can be received either locally from a vessel or remotely via satellite. The computer, located in the navigation bay, calculates the course to start the mission. At the same time, the scientific bay receives the configuration signal and prepares the specific sensors for sampling. The computer, located in the navigation bay, gives the command to move the battery towards the bow and retract the piston, which will permit immersion to begin. During the immersion, the glider is set to collect scientific data. The CTD allows depth and salinity measurements to be made. The fluorometer allows chlorophyll levels to be estimated. The oxygen sensor determines the concentrations of this molecule in the water column. All the data recorded by the sensors is stored on a hard drive. During the immersion, the navigation data is also registered. In shallow waters, the altimeter is used to avoid collisions with the seabed. When the seabed is detected or the depth objective is reached, the navigation bay gives the command to start the ascent. During the ascent, the glider continues to collect data measurements for temperature, salinity, and chlorophyll. The glider makes ascent and descent movements in the water column of between 0 and 1,000 meters on missions which can last up to 2 months, covering 24 kilometers a day in any meteorological conditions. In the case of an emergency, or at the pilot's request, the glider emerges to communicate with the base. The bladder inflates once again to receive the operator's signal. The glider transmits all the data collected, receives updates for the mission, and uses GPS satellite positioning to calculate its new trajectory before starting a new immersion.
Opa, só vou reposicionar o microfone. So I think that's now you understand better than my words to how gliders works, okay? And this is a model different than we use it here, but the mechanism is quite the same, okay? And this is one example here, the city of Cabo Frio, and this is one section that we got to measure temperature and saline profiles from a glider in a systematic and continuous way. These two characteristics are very important if you want to monitor any oceanographic phenomena. You need to collect the data always in systematic way, I mean, in the same regions, in the same points, and also you need to have these measures in a continuous way. Otherwise, you don't want to have, for example, the seasonal behavior of the oceanographic variables that you are measuring, okay? And this is very important for us, of course. So this picture that we're seeing here, these black points here, is represent one transmission of the slides during determined period, okay? So all of these points is a position of the glider that he just interrogates with the antenna in the continent and transfer all of the data that it acquires on the last dive for us here at the land, okay? This is the, how can I say, the dream world, okay? And this is the real world, okay? Not always is easy to pilot a glider because, of course, it is affected by the currents and the eddies and the whole dynamic oceanographic features that you have in one place. So sometimes it's different to maintain the glider in the section that you planned. But all of this data that it acquires outside the section that you are planning are very useful for us. For example, to be assimilated in our ocean model in order to better represent the present state of the temperature and the salinity field in this region, okay? So this was really done by us in this project that called Project Azul, that I call better about this project, I think that tomorrow and the day before and the day after tomorrow, okay? And this is an example of how you can integrate observation in an interactive way with oceanographic computational models, okay? Let's go. This is the kind of profiles that the glider could acquire, okay? Temperature, salinity, density. Here is the dissolved oxygen, sorry, the words are in Portuguese. And this is chlorophyll, and this is turbidity. All of these properties were acquired during the project that I told you about in this section, okay? And this is the glider working, okay? This red dot here is the glider going to deeper depths, higher depths, okay? And you see the temperature, salinity, and density profiles getting more deep, as soon you go to deeper depths. Don't pass this depth because our model goes only to 1,000 depths. But here you see profiles shallow, and now you see the profiles deeper, okay? You're going to 800, 1,000 meters of depth, okay? And now, after the glider acquires all of these profiles in this section, what can I do? Produce vertical sections, because things in the oceans is quite different than the atmosphere. Atmospheric temperature, humidity varies in a time scale very fast when we compare with the ocean. Things at the oceans are slower, okay? The time scales are slower. So you can use different vertical profile here to produce sections of density, of dissolved oxygen, of temperature, of salinity. So you can see now that one glider could produce the same product that the oceanographic commission, that a traditional oceanographic commission with an oceanographic vessel produce it. I showed to you in the first, in the third or fourth slide of our class today. So, and the efforts, the logistics efforts, the resource, money, financial resource effort was quite smaller than using a ship. Okay, it's this one example. That's why this kind of equipment is causing a big revolution in oceanography. And you can say even that this is a low carbon emission technology, okay? Because vessels need to burn oil, okay? So this kind of equipment doesn't need to do that. And you can see also some things like, for example, here for me is easy to see, okay? But here you have some isotherms, the lines of the same temperature in the left side, that are a little, how can I say, curved for the sea surface. This represents upward movement in the water column that is associated with the Cabo Frio edge, the cyclonic Cabo Frio edge in this region. You can see here clearly this also behavior in the isoalines, the lines of the same salinity here, okay? I know that it's not easy for you to see, but I can properly say to you that it's really happened, okay? And this is nice because the edges are not only oceanographic features in a two-dimensional that you can see only by satellites. No, it's a three-dimensional structure, affects the whole water column where they are happening. So with the gliders, we can see all of the water column also too. This is another, the seasonal density mapping. Of course, if I have the temperature and the salinity sections, vertical sections, I can produce by the means of the equation of state of seawater, the seasonal density mapping. And with the density mapping, I can have the distribution of the gradient pressure force. And if I have the gradient pressure force, and I know at the latitude where I am, I can produce, for example, I can produce the section of geostrophic velocity estimates also. So I can produce with the glider indirectly the distribution, the vertical distribution in a section of the velocity field. And this is very important also for evaluate ocean model results, or even assimilate this data in the ocean model results in a way to better represent the present state of the ocean, okay? Only to come back here, of course, if I have the temperature and salinity and the density field, I can also study, for example, the seasonality of the water masses that are present in that region. In this region, these gray lines represent the top and the bottom of the South Atlantic Central Water, a very important water masses that happen in this area. So you can see in different dives, different positions of this gray line. The red line represents the mean, okay, the average. So you can study also the seasonal variability of the water masses in the water column, okay? I cannot say about the masses that are in deeper region because the glider here only works until 1,000 meters, okay? So, yes, and you have the possibility to estimate volume and heat transports also. That is very important to understand many aspects related with the ocean's climate and consequently the planets and the Earth climate. This is another kind of autonomous surface vehicle. This is this is an autonomous surface vehicle. This model is called sail buoy. Is a sail buoy. It works with the energy of the winds. You really sail this equipment. You have one of these also here. This is an example of a mission that he just crosses the North Atlantic, okay, near the Ireland here to the Newfoundland banks here, Newfoundland banks. And here it works here in Guanabara Bay. This is the Sugarloaf Mountain, a very touristic place here in Rio de Janeiro. And here's our sensor that we acquired for one project. You don't know if you can see here, but this is a meteorological smaller meteorological station that it has coupled in order to help in the pilot. And also you can acquire data from wind field, pressure field, temperature field that could be used for different reasons, also in different goals in our project. This is some graphics that you can acquire, mainly related with significant wave height field, peak period. You can have also direction of wave fields. And during this project, we had also a buoy with a sensor called a wave hider. It's a very traditional sensor. It's a buoy fixed in space that acquires wave height and wave period and wave direction propagation. And you could compare the result of this traditional sensor with this autonomous surface vehicle data of waves. And the results was very good. So it demonstrates that it really has a very good potential to acquire this kind of data, wave fields, in our not only in our region, but in different regions around the world. This is the wave sensor that I just told you about. Sorry, let me come back. The wave sensor, okay? So it has an equipment called an accelerometer here. And with the accelerometer, he got to estimate the height of the wave, the period, and the direction also too. The older models was not prepared to acquire the direction of the wave, but now, since some decades ago, we have wave sensors that are able to acquire wave direction also too. Most of the time, they are near the structures that are floating over the sea surface, because monitor the wave field is very important for the life of these structures, okay? And this is the meteoceanographic buoys. I have already told about this equipment for you, and you can have many different sensors in this kind of buoy. This is a basic metocean buoy here, okay, where I'm with my cursor. So you have a traditional weather station here. You can see here the sensors that measures wind field, now wind velocity in 1 point, wind direction, humidity, precipitation, temperature, pressure, okay? And below here, you can have also accelerometer to measure the wave field in the area. And this one is a LiDAR metocean buoy. LiDAR is another sensor that acquires, using laser technology, acquires a vertical profile of wind field over the surface of the planet. So here, over the surface of the sea, okay? So we have different buoys with this LiDAR, and this kind of sensor is being used a lot today because of the wind energy potential over sea that are being very explored in different regions around the world, okay? This is a vessel that is needed to work with this kind of technology. So we can see different from the gliders, okay? The buoys need a structure of ship very big, okay? But in this case, I think that is not, you cannot substitute this kind of sensor. Buoys are very, very important, okay? Metocean buoys. This is the LiDAR, the light detecting range sensor that acquires the vertical profile of the winds. This is a sample of data sets that you can acquire with LiDAR, okay? It's a very important sensor, as I told you, related with energy transition, and especially to understand the potential of wind energy over sea regions. And this is an example of a metoceanographical buoy that has in a project here in Brazil called Sim Costa. And translating for you, Costa is coast, of course, and SIM is system integrated monitoring. So it's a system to monitor oceanographic conditions around the coast. These are some points where we have buoys like that along the Brazilian coast. And here's one that stays near the Copacabana beach. Okay, this is Copacabana beach, very famous around the world. And this is some intruders, how can I say in English? People that was swimming and takes the buoy to give a break, relax a little bit, okay? And this is the position of one of the buoys. As I told you, this is the Copacabana beach. And this is all the data that you can see in the sites of projects in Costa in real time. You can see many different variables, not only the oceanography one, but of course, meteorological ones. And that's it. But to end our class, I'd like to say something about the observation data, only to summarize a little bit the good things and the bad things, okay? The important thing to say that environmental, oceanographic, meteorological data are fundamental to understanding the ocean dynamics in different spatial and time scales, and also for evaluation and assimilation in numerical models, in ocean numerical models, ocean numerical physical models, okay? Need for long data series. This is very important. In the class of Liva yesterday, she told you about El Niño, La Niña, she told you about North Atlantic oscillations that are phenomenal that with a measure of 1 year, I will not be able to investigate the influence of this phenomenon in the oceanographic process that I want to study. So I need long period data series to understand the impact of, for example, of climate variability processes, okay? If I'm talking about climate change, of course, I need much more long period data series. So this is important to point that because you need to have a strategy in your country to put funds, resource in this kind of study, because we know that is very important for us for many different reasons, as the ones that we talk about in the beginning of our class related with sustainability of the planet. Low availability of oceanographic data in the South Atlantic collected in the systematic, continuous, and long period way. Now, bringing the problem for us, because we know that we are in a project that you are representing different institutions that deals with the Atlantic Ocean. So it's important for you guys to know, I think that you know that, but you have a huge difference in the availability of oceanographic data in the North Atlantic and the South Atlantic. Unfortunately, the South Atlantic, compared with the North Atlantic in oceanographic data sets, we are almost a desert, okay? And we need, if we want to comprehend all the puzzle, if we want to understand well what are happening, why things are happening in the North Hemisphere, in North Atlantic, we need to know well what is happening in the South Atlantic. South Atlantic exports heat for the North Atlantic. So we need to monitor well. So we need to have systematic, continuous, and long periods measures here in our South Atlantic. Of course, this is a problem as a whole, for the whole basin, and for the whole ocean, vandalism, especially in coastal regions. And the problem, of course, we have high financial resources, but we need to put this in the agenda of the different countries around the world. Oceans covers more than 70% of our planet. Things starts there, things could end there. These are the sensors that I show you. And so we have the gliders that, as I told you, are very important to be more used because they have, for many reasons related here, the high financial resource, so we can decrease the financial resource using traditional oceanographic vessels. I'm not saying to avoid oceanographic vessels. No, we still need to use them, but you can increase our power to understand the oceans if you use more this kind of sensors. Opportunity ships, this is nice. For example, we have a lot of transatlantic ships. We have a lot of commercial ships passing most of the time through the Atlantic. Why not install sensors in these ships, okay, to acquire the data that they are that they could acquire during this passage in the Atlantic. Okay, the effort is minimum for these ships. Okay, they only need to put a small sensor in one region and measure this for us, for the whole scientific community. Radar systems also, this remote technology is very useful also to understand the dynamics of the ocean without the problems of vandalism and the high financial resource. Of course, this kind of equipment is expensive, but if you think in using it for 2 years, 3 years, 4 years, it pays itself, okay? That's okay. And the other thing is to try to develop low-cost sensors. Here I put air quality sensors, but the Arduino technology, I don't know if everyone had already heard about, but Arduino is a technology that is kind of fun, not a nano technology, but a small scale technology that is very cheap. So of course, you need to have a lot of experiments trying to see the precision of this kind of acquisition of data, but I think that could be a development that you can invest, the science could invest in this in order to have cheaper solutions and to enhance the acquisition of data. Well, let's go. This is the reality. This is a little old, okay? Because the source is World Ocean Atlas 2018. But we have for about 6 years from now. This is what the oceanographic data sets that you have in the World Ocean Atlas, okay, in 2018. The red areas, of course, you have a lot of density of oceanographic data. Take a look at the South Atlantic and the South Pacific. You can see more blue areas than red ones when you compare with the Northern Hemisphere. Okay, these are the types of oceanographic cases that you have. Okay, so I can say to you that in 2018 we have less than 5% of observations that you have in the whole world ocean in the South Atlantic Ocean. So we need to take a look with more detail to this ocean. These are some projects that you have here in Brazil that are very important for us because they feed us with very important information about the ocean behavior along the Brazilian coast, okay? All of these gray boxes here are projects managed by Brazilian Navy, and in the right side, we have project managed for different research institutions here in Brazil. And this Projeto Costa Norte and Projeto Azul was example of 2 R&D projects that was developed inside our laboratory. I will tell with more detail about this project in our last class. And that's it. Involvement, continuity guarantees is important. Need to integrate the different observation efforts around the South Atlantic and the Atlantic as a whole is very important, because only with this integration of observation, we could really understand all the puzzle and all of the dynamics of the Atlantic Ocean, best practice always, and the involvement of the local communities and ocean literacy. Here, what we are doing now with the class of you, of course, we can think in doing this kind of efforts with the local communities that even don't know the importance of the ocean in their own lives, okay? Maybe a person that lives inside, in the middle of Brazil, don't know why it's so important to study the ocean for their life. They don't know that the ocean has a very important aspect related with climates of the earth, okay? And they need to know that. And they only will know that if we have an effort of take this information to them, okay? And of course, if you have problems with oceanographic data, imagine the meteorological data sets. It's even worse for us here in South Atlantic. And I think that's it. This is only a summary about related with the remote sensing, what we can have with remote sensing, and it's very important for us because this data could be also assimilated in our ocean models and could be used to evaluate the results of our ocean modeling. It's important for coastal and offshore monitoring, for example, to avoid problems related to fire spills. It's important to increase the frequency of the data sets that are acquired. In fact, the ones that are publicly available, because you have the opportunity to acquire buying images of satellites, but it's very expensive. And these things is more technical, need to adjust algorithms for local conditions. This is more specific about the people that use reactive remote sensing research area. And that's it. This Livia carefully prepared this slide. I think that is important for you guys. These are some places in the internet related with some research institutes where you can acquire this kind of data that I'm showing to you in a freely way. It's freely for all the scientific community, all the community as a whole. So you can see NOAA, you can see Aviso, altimetry that takes a lot of data from satellites, the National Data Biocenter, the National Snow and Ice Data Center. Some of these places you can find also products related to numerical models. And that's it. If you have any questions? Are you there?
Yes, yeah.
So, Livia.
No questions? Okay, great, guys. So this was this list. This was just an additional comment. This list does not exhaust all the options you have to access and download, absorb the data. Okay, it's just a few places that you can find data. Of course, if you search through the internet where to find BUIOS or for the project name, I'm sure you'll find a lot of other options. Okay, but these are some that you can search. Okay, so
Can I ask one question? I'm sorry, Livia. I realize I do have a question. My question is, having heard about all the technologies, I'm wondering, for instance, gliders, they sound superb. You know, they're autonomous. You just give them a command and then they do what you want, and they can have all sorts of sensors. Why do we still have those, classical oceanographic vessels with CDDs and, bulky things, and you need to get a ship out? And why not just use gliders? Because they seem like an ideal solution.
We still have some limitation of some sensors in gliders. For example, we don't have a consistent sensor to measure velocity on glider. This is still a thing that is under development. Okay, we can acquire some seismic data in the gliders. This is one thing. So we still have some limitations to put sensors in the gliders. This is not. I show to you the beautiful world. Okay, but it's still very useful, and it's really causing a revolution in oceanography. But we still have some limitations. Of course, you're gonna have with the technology developments, these things maybe in the next few years will be solved. But remember that there are things that we still need the vessels, and I think that this will be also a transition. Okay, not be like the energy transition. I think that you're going to have a transition also. I don't know. Sometimes I take care to say these things because people that are more traditional in this kind of uses the oceanographic vessels say, oh no, you still need to use the oceanographic vessels. Yes, of course. But yes, for some purposes, the gliders will be, in my opinion, would be a not only more intelligent, but a more sustainable way to acquire data sets, ocean data sets. And the price, somebody, I think that Olivia just put, I don't know if it was related to these comments, But you know that in Project Azul, we acquired 5 gliders, and in 3 months, we lost 1 glider. 1 glider cost us a little bit, the one that we acquired, $200,000. And then he said, oh, you lose it. Yes. But the 3 months that the gliders produces of data sets, it paid itself. Okay. Imagine that you need a ship acquiring data for 3 months with a tripulation of 20 guys, 30 guys. Each day you won a lot of money. You need a lot of money. And if you sum all of these days of oceanographic cruise, you pay the glider 2 or 3 times. Of course, we didn't want to lose the glider, but things happen.
Things happen. Yeah.
Yeah.
Just an additional comment on that. Yeah, maybe if we think only about temperature and salinity and those sensors that the glider carries, yes, it maybe it's good on its own, but oceanographic vessels can do a lot of other things as well, like collect water and collect small organisms, so you can study them. Geological, you can take samples from the bottom of the ocean for geological purposes, and all of that. There are oceanographic missions, if I can say so. There are only for geological purposes, so they image the imagine you reach the bottom of the ocean. They can with some sensors that we're not gonna cover here. They can image from the bottom down, so a big layer of rocks and different kinds of rocks that you have, and that has relationship with a lot of things, including oil. So but yeah, it's a very expensive mission. They are very expensive, and they need to be think very carefully, so you can make the most of it.
Yeah,
right?
yeah. We must understand it because I don't know what I consider myself. I usually consider myself as a physical oceanographer. Now I don't know very well, even if I am only oceanographer, because I deal with many different areas of research. But my graduation was in physical oceanography. But we must know that oceanography and ocean science as a whole is composed by different areas of research. And of course, I keep an eye only on the applications that I deal with. But as Livia said, if you have some geological studies, some chemical studies that you need to acquire some samples, of course, all of this with the technology development could be inside an autonomous vehicle, okay? But this is not gonna happen next year. Maybe in the 1 decade, I don't know. And so we're still gonna need this kind of vessels.
Of course, and if you think about, we came already a long way, because in the past we used to use divers to go to the bottom and grab stuff, for example, and of course this was limited to a very shallow area. And now we have some autonomous robots, but they are still connected to a ship that can go to the bottom and grab stuff and samples. And so we are evolving, technology is evolving, and I think it's always going to evolve. And we can do more with less, which is good, since we can emit less of greenhouse gases and stuff. But we still, I think today, these different ways to observe the ocean and the atmosphere complement each other. So
that's it.
Yeah,
Thank you, guys.
No problem. So I have a small suggestion to propose to you. So if you can say no, okay. So we are getting close to our big break here. So maybe it would be better if we maybe finish our practicals from yesterday before we start, because we have another part of lecture today. Otherwise, it's not gonna we're not gonna have enough time, so we can maybe have the second lecture during afternoon. Yeah, I think I have an audience here.
Have the needed votes.
Yeah, go ahead, Nina.
I was just wondering when is the best time to ask questions about the challenges if we need help.
Okay,
you?
maybe we can see them now as well, so we can maybe solve questions and maybe go over the practicals. Yes,
Yeah, sounds good.
until yesterday, so it doesn't get also too far from what we've seen, right? So let me just adapt here. Okay, so I think the camera works fine. Let me just exit here. Okay. So let me just share this again. I'm gonna, before Luis Paulo was started his lecture, I think Sonia asked me to check something on the challenge that I sent you. But I know you put that on chat, but I lost connection for a while, so I
It's
don't
just
know.
on the coordinates.
Can you see my screen?
There's 2 times south, and there's probably one of them is a north.
Oh, this 24.5 to 23.5.
Yeah.
Yeah, no, they are correct. They are the same. This is the same area from practicals 1, topic 2, if I'm not mistaken. Is a very small. Let me open this here.
Okay, so it's just that smaller
Yes.
area. Okay.
Yeah, it's a smaller area, so you can download the whole water column. See, it's the see here. It's the
Yeah.
same area here. This small one. Of course, it's just a suggestion, because so
But
you would.
but in the picture of Copernicus, you have actually north, south, west, and east.
No problem. So if you want, you're not gonna use this index here. If you are, so that's a very good question. If you are only on the south hemisphere and you want to work only on the southern hemisphere, you put negative numbers. Okay.
Okay.
On the south and on the north, let me just show you this here. And the same thing for the west. Okay, if it's everything is to the west, you put negative numbers. So do you see here? Let me just. You see here?
Yeah.
Everything is negative, so it's a little confusing for those who never worked with that. But yeah, the thing is, if you were working on southern southern part of the world, you put only negative numbers, and same thing to the west, so you put negative numbers. Okay, so I
It
guess
was just confusing because it was
Of course.
No, the negative part, I understand that is different hemispheres, but if you want to do like an area or a square, you must have like north, south, east, and west. And when I have 2 times south, I was like, is this number or is this number the one of the
Okay.
vertices? So 2 times south, I was like, is this a line?
No, but please tell me if you find any kind of typos that you may think you have, because well, of course, you can make mistakes as well. But it's that if it's to everything on the south, you put only negative values.
Actually, on the when I was asking my initial data and I found that error in my coordinates, I already could run with one. So I think I did the map good. I think it's the same area as this very small square.
Yes.
And but then I have difficulties in plotting the vertical levels because I think maybe some of the data set I'm importing is the not right one. So the outputs I'm getting is outputs from the practicals, not the ones that is like giving me the results from the area of the practicals and not the area I'm trying now. More or less this.
Can you show me? Maybe we can solve
Yeah.
this.
Unless they have the same the same graph plot, but I don't think so. So everyone is saying
Yes.
okay. So I guess it was supposed to be like this. Okay. So I did for salinity and temperature, so both of them are equal.
Okay. Great.
And I did try to mix colors to try to experiment this.
Yeah,
And then I tried to do this, but it runs, but it gives me the same results as the previous coordinates from the practical. So I don't know what I'm doing here wrong, but
Okay,
I cannot find.
Okay, so maybe you're loading the data from before and not the one that you downloaded. Can you show me the name of the file that you downloaded for that challenge? Or when?
This
Okay, so you downloaded with this script?
Yes.
Okay, so at the end of this cell, there should be
Here?
Yeah, so you see at the very much end, there's F with a click, and you have Kimems _ South Atlantic or SA underscore var name
Okay.
time dot string f time. So this is how your file is going to be named when it's downloaded. And you can check if you are when you load the data that you want, you are loading this file. You can scroll down a little bit to the part where you load data. I think you've already.
Is this one? No.
Yeah, you should have loaded before, so you could plot the map. Okay, so plot the map. So what data do you use to plot this map on this cell? This cell there, just scroll down a little bit more. Okay, so you put manually
Yeah, it was not working, so I tried just to see if it was right. The thought
Okay.
I had.
No problem. But the thing that we want to test with this figure is that if you downloaded the same area as you requested. So
Okay.
what would be more interesting to check that is to use the values from the data you downloaded instead of putting the same geographical limits that you requested. I don't know if I'm being clear.
Yeah, I just don't know because this one was from the same resolution but not the same area. So I'm kind of
Okay.
confused which data do I miss here?
Okay, so first of all, what I would suggest you is that can I make a drastic suggestion for you?
Yeah.
Start over with a clean script,
Mhm.
and so you can put and can check everything that you are doing and the geographical limits, because sometimes it happens to me a lot. Sometimes when I'm doing things and I'm going wrong and I erase and write it again and I erase and I write again. At the end, I don't know what I'm taking and I'm calculating. So what I do is that I start out all over again. So my suggestion for you, because I think this could be more clear for you, is that you think
I
you
don't know if it's hot
no,
because Janice
that's totally okay. Thank you.
started talking.
So start new, start fresh, and then you can copy from what you already have to this new notebook, which is called this script. It's a collab notebook, and so you can. I think it's gonna be better so you can put exactly the geographical limits, and then to get data from, and then load the data and then get the information from the data, so you can, I think it's gonna be easier, because what I think happened, and it happens to every time for me as well, is that you start with one thing and then changed, and then something is confusing, because I think you're getting data from one place and using as another thing. I don't know if I'm being clear
Yeah,
here.
but
So what I suggest to you is to start fresh and try to perhaps now that you know that you have in the same script now that you're showing me, you have two ways to download data. You don't need these two ways. Just so choose one and try to download the data through this just one. And so you can, I think it's going to be cleaner, and I think you're going to find what you're doing wrong. And if you want to, at on the afternoon or tomorrow, we can revisit it again to see if you got it
tomorrow
right.
it would be complicated. I have the presentation.
No problem. We can do that on Friday. Don't worry about that. Okay. Just I think it would be best for you to start over again so you can understand exactly what's happening, and we can revisit this whenever you need. That sounds
Okay.
good?
Yeah, sure. It just let me ask something. Is this the global data set?
Yes,
Or
this is a global data set, but what we are doing here is that we are taking just a subset of this data.
so after I put this, supposedly I should just only have the data for this. Or
Yeah,
not?
because you are defining their low min, low max, lat min, lat max. You are saying to the data, I'm gonna access this global data, but I only want this subset. this part.
So probably the error is not here, is somewhere else.
Probably not. Yes, probably. What I think is it's happening because you have more than one type of ways to download data and more than one places that you are downloading data. Maybe you were reading something else that you shouldn't, reading a wrong file.
Okay, but there's no problem in like doing for one of the variables and then from the other, or should I put it
No.
together?
No, there's no problem. That you could put together, but you can do it separately because let me just show you. When you have requests and you have SO underscore 0.0.
Sorry, I stopped the.
No problem. Can you continue to?
Yeah. Now should be working.
No, I can't see it. Oh, I think it's coming. Yes. So there, when you have set parameters for each variable, you have requests, and then you have SO underscore 0.25.
Yeah.
You have dataset ID. This is the ID of the product, the result that you're gonna access, okay? And vars, it's the name of the variable inside that product.
Yeah. I went to check that they were different for Salinity.
Yeah.
One resolution and the other.
Yeah, just like we saw yesterday, right? So the following block here for the other product, it's independent from this first one. So if you want to, you can put temperature here as well, if you want to. Okay, but if you want to have both two of them, one for salinity and one for temperature, it's gonna work also. Okay, what I'm saying that is what we saw before our lectures started, is that you have another way to, I don't think you still have that in it.
Yeah.
This one. Yeah, and maybe, and if you, I don't know if there are some differences in areas, so you can be downloading a lot of different data. And you can read different things that you should.
Okay, I actually did like this in a way, and then with the other without. So if I did with this process, I did not put running this one, and they were giving me the same. I guess because the plots and graphs were the same. There was no change. So I guess if the mistake was in one of them, should already be incompatible values from one way or another way. But since they have the same data set and all, I don't see how they could change.
Okay. The thing is, we have to search where the error is, and that's called debugging, because it's to find bugs and erase them. It's common in coding, but when I would have to search through your script, and I can do that, no problem. But what I suggest you before I can do this for you to find the error for you is that you start over again and clean it up a little bit, so maybe it's gonna be clearer for you as well. And then if you still having problems, we can do that on Friday, no problem. We can go step by step to figure out what's going on. What do you think?
Okay. This part of Gemini is not a prerequisite for the others, or is it? Because I did not see much here. I
Okay,
think
this
it was
was
just an example.
Yeah, this was just an example that we ended up doing
Oh, so,
yesterday,
okay.
and I left that there because so you can, if you want to test
Okay.
Gemini.
Okay,
no,
thank you. I will do the suggestion.
no problem. So anybody else has problems with any challenge? Want to?
Yeah, I just have a quick question. Hopefully, it will be quick. It's on the code that we need to do with El Nino and La Nina.
The first one, the
Yeah, the first one.
topic one. Okay.
We need to kind of import data from ATL3 regions, and we didn't do that in the practical, right? I mean, we don't have those
Can you
data.
repeat the first part? I'm opening the practical, the challenge here. Let me just maybe share that with you. Okay, this challenge, right? So
Yeah.
you have some questions.
Yeah.
What is that about the questions or the second step here?
No, the second one, because they're like talking about the ATL3 index.
Yes.
And I'm just wondering how we can import the data from this, or like how it works.
Okay, so no problem. So the data that I'm suggesting you to use, which is the same one that we used in practicals, it's global, okay? So remember that we did global maps on practicals on the day one. Let me just open here so I can show you.
Yeah, I know I imported the data, the global ones, but when I'm trying to plot and to do I did the little square in the Atlantic for El Nino and La Nina, but then when I tried to import the sea surface temperature data, it says that there is no data for ATL3 index or something like that. So
Okay, can you show me?
yeah, I can try.
Let me just let me stop presenting.
Can you see now?
Yes.
It's a bit messy, so I did like all the first parts the same as that's what we did. So it's exactly all the same.
Okay.
Then I plot the map with the ATL3 region.
Okay.
And I had the map.
Okay, great.
But then when I tried to do the sea surface temperature, tried to use Gemini and stuff, but then it just, it doesn't work. It's red here.
I think I know what went wrong. Oh, this okay, this cell there, it worked or not? Yes, because
This?
this
Yeah,
one
yeah.
worked. Okay, so you didn't have any problems to select the area. Okay, it's just to plot. Let me see slowly your you can scroll down a little bit. Okay. Okay.
Could it be the difference of systems from longitude and latitude? Because I did with, I remember it was 340 and 360 instead of 20 and 0. So for me, I think it worked because it showed me this exact same area, but with the cool, warm method. And then La Nina and El Nino showed different different El Ninos and El Ninas from the El Nino region that we practice. So could be the system is changed?
Yeah, that was my suspicious as well. If you recall from practice, from the first practicals that we went over this data. Remember that the longitude is not from minus 180 to 180 is from, if I'm not mistaken, from 0 to 360. So you have to convert these numbers so you can get the same area, the area that you want. So that's why I think this error you're getting. Sonia, what I can suggest both of you, and I think it could be good for both of you, is that maybe you can exchange messages and
Yeah, we can do
maybe
that.
you can help her
Yeah.
so you can talk about it. So I'm not, please don't get me wrong here, I'm not refusing to help, but just
Yeah, no worries.
try to learn on your own and help each other.
Yeah.
So the same suggestion as I made to Sonia, maybe try to work it out together, and if you can't, we can revisit this tomorrow or on
Okay.
Friday. What do you think?
Yeah, sure. And then we can move on to the practical 3 that we did not
Yes.
finish.
Does anyone else has any doubts about the challenges, or yes, go ahead, Olivia.
Hi. I haven't started the challenges yet because I'm still trying to get my head around some things on practical 1 of day 1.
Okay.
And I was trying to understand when it comes to the calculating the anomaly and climatology, because these are quite new things for me. Maybe I can share the screen
Yes.
if I manage. Where is it?
And just get my water. Just
how do I share the screen? Okay, can you see my screen?
yes.
Okay, so here, okay, we're getting a time range, and then we're grouping by the months, and then we're calculating the average. So we're ending up with 1 value per month. Yes?
Yes.
Okay. And then over here, we are actually calculating the average over all the months for every cell, like lat and lun. Yes?
So we ended up with just one value.
Exactly, with just one value. And then here we're just taking the original, no, not the original data. We're actually taking the average over the months and deducting the climatology.
Yes.
Okay. So where I got confused was in here, because this should be the same as the one, I mean, or could be, right? Could be the same as the one above. The difference is there is no slicing here. So this is compute the climatology for the whole period.
Okay. So I think I know why you're confused, because I think I confused you on the first day. Remember that I had some problems because I wanted to do something and it wasn't working, and I ended up doing more than one type of anomaly. And I confess, I think I confused you. So maybe forget about the first part, the first one. Yes.
This one, okay.
Because this is only shows actually, if you plot, you're gonna see how actually the climatology months deviate from the average value of climatology. So I have this period there, 1991 to 2020, okay? and I separate per month and make an average. So at the end, GB has 12 months. Okay, and then I take this GB and I average the whole, all of the months, the 12 months. So SST underscore climb has one value. Okay.
One value per letlon. Exactly, yeah. So
Yeah.
the months are kind of removed. I mean, or we
Yeah,
we end up with a two-dimensional array.
Yes, because I take 12 values and I average them. So I just have 2 dimensions. Okay,
Mhm.
because I only have one value per dimension.
Yeah.
You understood. Then what we did was SST anom equals these 12 values, and then I subtract from this one value. So at the end, I end up with 12 values. There are subtracted from the average of these 12.
Yeah.
So what it means is that I have climatology anomaly, because I have, if you plot the time series, I have a climatology anomaly. What it means is that it represents how much each climatological month I have from this period, 1991 to 2020, deviates from the average value. Okay. But for us to evaluate El Nino, we don't want that kind of time series or that kind of anomaly. We want whole time series with months and years, and we want the anomaly of this whole period. So this is, and then because I wasn't at the time getting it right to perform the anomaly of a climatology for a specific period. We did a second part.
Sorry to interrupt. So this one is correct or no?
It's not incorrect. The calculations are not incorrect, but they are not what we are going to use to evaluate El Nino. Okay, because at the end we just have 12 months, and we don't want that. We want the whole time series. Remember. What I'm trying to say here, maybe I'm complicating even more, is that on the first day when I was doing practicals with you, I was a little confused, and things were not working, and it ended up confusing you even more. So I would say to you to ignore this first part, okay? And you can do the anomaly by this that you're showing me, because once it's for a whole period, but the best one would be the following one that we did.
This one?
Yeah, because yesterday I corrected it and we saw it together. I don't know if you were present, but I think so. Because I was able to, I can explain to you again. No, there's no problem. So this first part, climatology period, I just separated this period for, that will be my climatology period. Okay, so far so good until here, climatology period. Yes or no?
Yes.
Yes. Okay. I'm just separating. I'm just taking a slice of the time range I have. Okay.
Yes.
The second part there, group by month and calculate the mean over the climatology period. I get this variable that I just created, climatology period. I apply a group by per month, and I average. So climatology gives me 12 months, okay? So now I have a climatological year. I have a climatology made up of 12 months, okay?
Mhm.
Okay. So this third part now is where I was doing things in the wrong way. So what I want to do now is I want to take my whole period, I know almost 500 months, and take the average climatological year, which means that I want to extract the average values of each month from the climatological month, who is made up of this period on the first part, 91 to 2020. Okay, so what I was not doing right is that I was doing just DS minus climatology. And because climatology, if you if you want to comment each part and see what each part produces, climatology only has a time index called month. It doesn't have time as an index anymore. And what I call an index is that when you see on the bottom here, dimensions, you have latitude, longitude, and time. So our original data has time as a time index that is called time. Maybe this is confusing as well. So when I was doing just DS minus climatology, I ended up with something weird because climatology doesn't have time, but DS does. So I ended up subtracting different things. What I had to do is take DS and group by month. Take it and group everything by month. So that way I create an index for time called month. And it's not an index for time called month that has only 12 values. It has 12 values for each year of all of my years that I have. So what it does now, anomalies, it takes the index, the time index called month from DS that I just created, and subtract to the index month from climatology for each year. So when it starts, if I'm not mistaken, at 1982. So January 1982 minus January from climatology. February 1982 from February from climatology, and so on and so forth until we reach almost 500 months.
Okay. And this also confused me a bit because the mean, why do we pass again time here? Because at the, for example, in, where is it? In here, for example, we say group by time month, but then we don't say like this, right?
You try to run it, it's going to be the same thing.
So it's the same thing though?
Yeah, if I'm not mistaken, yes. You can try it now. Oh no, you can. Oh, that
What
doesn't.
do
Why didn't it? Okay, so yes,
because we're disconnected, I think, from the
yeah, you had to maybe download it again.
everything.
But,
So those two functions are the same, like dot mean or dot mean time.
yeah, because I was doing everything on the same line, I was grouping by time and then taking the average of that grouping. So that's why it knows that I'm grouping by time. Okay, but you can test if it
Okay.
yeah
I
if
remember
it
what happened.
yeah.
Okay.
The good thing about Colab is that you can test if something works or not. If you want to like comment the second and third part, you can see when you put just the first part here, climatology period equals something something something. I'm creating a new variable, and when I put just the name of the variable after, It's for me to visualize how it went. But the thing is, it only gonna respond if you put several variables to see, like this. I have climatology period, climatology and anomalies. It's only gonna show us the last one. So it's showing you us anomalies. But if you comment the other ones, it's gonna show you climatology period. So you can do things and check the status of each cell that you run. You
Yeah,
know,
that's what I was trying to do. But then I got confused. So
okay.
I
That-
have a copy of the notebook, in fact, and I think I have to start afresh as well because, for example, this graph, where is it? This plot here is like it's not resulting as this one. So I guess I have to just create a fresh copy and yeah, and just try it. But that's what I was trying to do, to try and understand bit by bit what is happening, because I don't know if I should try to do this or I just should carry on and start with the challenges.
you know, as we said yesterday, our ultimate goal here is for you to learn. So, of course, if you want to test it out, go ahead, because you need to understand this to perform the challenges. And another thing I would suggest you to start fresh and to try to understand things on your head. And I apologize because I was the one who confused you all. But I hope I could clarify some things now. But if not, we can still keep going over this. There's no
No, it's okay. I think I got it even until I digest a bit the information. If anything, I will ask again tomorrow.
Of course.
Thank
So, okay, thank you. Do that. So this is coding is like that. Okay, you maybe at first you don't understand much, but then the more you see things, the more you try to do, the more you understand and things start to make sense. So again, be kind to yourselves because we are on the way. All right. So okay, so any more questions about past practicals or challenges? No? Okay, so I think we can go over a little bit of our practicals from yesterday. Let me just share this. Does anyone want to tell something? No? Okay.
I just want to ask a very, very quick question without regarding the codes or anything. Is just do we have another form of save the collabs rather than in the drive, because I'm getting without space and they already know no automatic saving.
Okay, so you can download them. You can come here and download them as I suggest this one, iPy Notebook, because you're gonna save a file with that extension .ipy nb, and then if you want afterwards, you can just upload it again to Google Colab, and it should work perfectly again.
Okay.
Okay. All right. So, do you see my screen? Okay. Yes. Okay. So let's go very quickly go over some things that we did yesterday. So we're gonna evaluate temperature distribution with two different horizontal resolution model results. And these are the geographical limits. I've already done the importations and I've already downloaded data. Let's hope it stays that way. Create in and out directories. Please let me know if I'm going too fast. But this part we already did. Download the data is the same thing as before. This is an example of how to use Gemini. I'm gonna leave it here. So here we plotted, it's not showing, the downloaded area. Okay, and we saw that it matches both areas. So here we plotted the vertical levels for each data, and we saw some difference here. And I think we got this far yesterday until here. Do you have any doubts, any questions? No? Okay. So now let's plot a map of temperature for both data sets. It's very similar to what we've done for practicals on Monday. Okay, I think topic 1. So, and we are going to perform an average over time and over depth. Okay, so remember that we have a 4-dimensional variable of temperature. I have longitudes, latitudes, I have depths, some values of depths, and I have time. I have 1 year, remember? So if I want to plot a map with a 2-dimensional figure, want a longitude, latitude map, I have to somehow select or average or calculate some things with these other dimensions here. I can't, Python is not going to understand if I try to plot a map, which is 2D with a 4D variable. So what one of the options here is to perform an average. Another one is, and we did some things like that, is to select time range, or to select depth range, or just one value of time or one value of depth. So our final data that we're going to plot is just 2-dimensional. Okay, but here we are going to perform an average over time and over depth. Okay, so these are my 2 data sets, remember? And these are the variables inside each data set. Hope you remember that. And then I'm just defining the average over time and over depth for both of them. And I'm calling, and I'm giving these names to them. Okay. Here's the part that I'm sure you remember to define the limits of the map that we are going to plot. Okay, and we are going to plot 2 maps on the same figure. That's why I'm defining subplots here with 2 lines and just 1 column. And then we're going to change. We're going to plot with 1 line and 2 columns, just so you can have more than one example of how to do it and how can you manage these kinds of figures. Okay. Here I'm adjusting the space between the subplots, so nothing goes over, so one doesn't go over the other. Here I'm just defining the latitude and the longitude variables, okay, just to save, so I won't write this whole thing when I'm gonna plot. It's just to make the code cleaner, okay? again, it's not mandatory, but it's a good practice to always have your code as clean as possible. Okay. And this is my temperature, the minimum and the maximum values of my temperature. Okay. So here I'm gonna plot the temperature for the first data set. So longitude, latitude, and temperature. I'm saying here what color map I want it to be colored by, and my minimum and maximum values. And I'm saying that I want in the projection, the same map projection that I defined on the beginning. Okay. Then I'm setting a title here. This would put a color bar for this figure, but I'm just gonna, if I'm not mistaken, if I can remember correctly, I'm just gonna have one color bar for both of them. So important detail, when you have multiple subplots and you want to have just one color bar for all of those plots, it's important that all of them have the same limits. Okay, otherwise you're gonna plot one figure with one limit and the other figure with another limit, and the color bar can't have both limits. If you want just one color bar, everything has to be on the same scale. Okay, so here we are adding map features. Okay, so the extent, the coastline, borders, coastline again, I'm not sure this is needed, but I put it anyway. The land. Let me know if something feels awkward. Okay, we can stop and start over again. And some grid lines. Remember the grids from the grid lines. Okay, so this is the plot for the second data set. It's the same thing, but for the other data set, notice here the variables names, the same color map, and the same limits. Okay, and now a different title. So this would be if you want to put a color bar to the second data set plot. So the same thing here, add features, add grid lines, and now I'm adding a common color bar for both. And because I have, why I have to do that separately, kind of, it's not the color bar from the first and not from the seconds, that here I establish the position where I want to put it, okay? And I encourage you to change those numbers, change your way to see what each one does. I put here a legend. This one says how much left, when it starts, the bottom, the width and the height, the width and the height. So you can make it bigger, smaller, wider, or not. You can do something. You can set it up like this. I'm saying here that I want I want these limits of the color bar and the colors to be how can I say, linked to this figure here, which has the same, again, has the same limits and color map as the first one. So I won't have problems here. The same axis and my orientation. I put it on vertical. I could put it horizontally as well, but I would have to go through this. And my label for my color bar. Let's see how it did. So here's our figure. Let me just open it in a new separator. So we have here the temperature distribution. We can see higher temperatures on smaller latitudes, and and lower temperatures on higher latitudes, which is expected. Okay, just like we saw in lectures. And I don't think there's much more to see here. Do you have any questions, any comments about this figure? Or can we move on? You can, I can see the meet if you can open your microphones. Okay, go ahead.
Just one question. When comparing, like visually, there isn't a huge difference, right? Or I'm just asking to make sure that I'm not missing anything.
Yeah, no, there's not much difference.
Maybe
Right
at the bottom.
Yeah, you know why? Because it's a very big area. Okay, so sometimes those differences to in very big areas where things doesn't change that much. Remember, on the ocean interior, things doesn't change as much, so we don't have much difference. But you see here,
Yeah.
it's a little bit different than here, so you have some differences here as well. It's very subtle, but you have some. What you can do to see a difference, maybe choose a spot in space, the same spot for both of them, and may plot a time series to see if there's much difference. But remember that we are not here here. We are just evaluating different horizontal resolutions. It shouldn't be that much difference between them because it's temperature. They shouldn't have results too much different because it's a very good model. It's a reanalysis. It has a lot of data on it, so it's gonna be very well. It's gonna have robust results. So the differences are maybe not that big, which is good, which means that maybe if we don't need that much detail, we can use the 1/4
The course
degree result, okay, instead of the other one, because it's always going to be bigger and heavier, the file. So things that you need to think about. And so when you do kind of these evaluations, you notice that, okay, so I don't, for my purposes, I don't need to have the best ultimate result because it's going to be heavier, it's going to be more expensive computationally. So all the things that we are discussing these days, it's something that we see here on practice. Okay. Was that it?
Yes, thank you.
Okay, no problem. So now this one is almost the same thing, but as I told you, I'm changing here. I'm plotting subplots with just one column and one row and two columns. So now the maps are gonna be side by side. Not much changes. Okay, the same limits, the same latitude and longitude variables, the same way to plot. Okay, same everything. I'm gonna, what changes now is that here I have a horizontal color bar instead of vertical. And if afterwards you want to check, those numbers here are different because otherwise I would have on the horizontal color bar like this and like this, and it wouldn't make sense. So what we have is this. Let me just open it. So it's the same figure, okay? But for me, at least, I like this type of visualization better than the other one. But again, it's just a choice. So what I'm doing here is just showing you two different ways to plot the same thing. And we practically just changed the display of the figures. Okay. Okay, so next we're gonna identify locations of maximum and minimum values. Okay, so we are gonna calculate the minimum and maximum values for each data set. And we are gonna identify the geographic location, which means the latitude and longitude of those values, minimum and maximum for each data set. And we're gonna create a table to show the results as a pandas data frame. We're gonna work a little bit more with pandas data frame for the practicals of the Luis Paulo lecture from today, but later today. And we're gonna save these files so we can use it later, okay? So let's go step by step and please let me know if I'm going too fast. So here, the same thing, I'm establishing the average temperature for both data sets on time and on depth. So I only have a 2D variable. And here you didn't, if you don't want to, you don't need to do that, because you can search through all the 4 dimensions as well for the minimum and maximum values. But here I only work with a 2D map, so it would be easier, okay? Otherwise, we would have to work with 4 dimensions. So here, okay, go ahead.
Sorry. So in reality, we are actually getting the min and max of the average values, right?
The average on the time and the depth. We are imagine this map here that we have. We're gonna search through this map, these 2 maps, where the minimum and maximum values are. Okay, for this average in time and water column. I don't know if I was clear.
Hi. Yes, thank you. Sorry, my internet connection got
No
stuck.
problem.
Thank you.
Okay, so here we defined our variables, our temperature variables, as an average in time and depth. Here we are gonna extract the minimum and the maximum values. So I define these variables right here, and I take the same variable here, and I apply. I'm saying here I want the minimum, and I want just the values instead of all the attributes. So I'm just gonna here I'm just interested in the number. Okay, the same thing for minimum and for the 2 products. Okay, so here what I'm getting, and I'm taking a different type of argument here, as I'm gonna, what it means, arg mean, is that I want the index, which means the locations of latitude and longitude, or actually not the locations yet, but the element in both directions where I find the minimum value of my temperature. Okay, and I'm saying I want this regarding these 2 dimensions, which means it's gonna, for example, I have dimensions latitudes that has, for example, 100 elements, and my latitude goes from 0, -10 to 90. These are my values of latitude, but my list if you want to think about lists or an array, has 100 elements. Okay, has 100 numbers. Okay. And what I'm saying here, I want you to tell me in which element of latitude and longitude I have my minimum value of temperature. Okay? Or confusing? Confusing?
Yeah, it's a bit
So
confusing.
yeah, so how it differs from the previous.
Okay, so here I'm taking the values of the maximum and minimum temperature, which means is that, for example, here the minimum that I've already, let me just, so I ran this, so my minimum temperature value for this product is that number, okay? Same thing for my maximum, okay, is that number. What I'm getting here, let me see if it's easier. So I have, let me see. I have an information of, in my latitude, where that minimum is located, and the same thing in my longitude. Okay, so let me show you. This is my temperature that we defined here. So I have longitudes and latitudes. So do you see here, I have 241 values of latitude, but it's not values. I have 241 elements in my coordinate latitude, but the values of my latitude are these ones. Okay. So when I ask him to give me the arg min regarding latitude and longitude, I want him to search which of these elements that correspond to these values, both of these values here, corresponds to the location, corresponds to the value of the minimum temperature that I've already got, that I've already created or extracted here. Too much, right?
But it was better now to understand.
What?
It was better now to understand using the.
Okay, yeah.
Seeing the difference between elements and the numeric values.
So now we know this is how much elements I have within my coordinates, okay, both in latitude and longitude. And these are the values of these latitudes and longitudes. If the same thing, let me get here our original data to show you the difference. So the same thing happens to the other coordinates. I have 12 values of time, 4 values of temperature, but my time is not 1 or not 2 or 10. My time at index 0, for example, is this one. So this is what means to work with index. For example, my time, my depths of index 3, because Python starts with 0. So 0, 1, 2, 3. This is a little bit confusing at first. It's this one, okay? So this is the difference. I have 4 elements, but the values are the ones inside the coordinates. Okay.
So if we go back to the min temp index in the code, where you have the argument, that
Here?
yeah. So whatever it returns, let's say it tells you, okay, it's in location latitude 1, latitude element 1, and longitude element 10. If I go to that index, I will find this minimum value.
Yes, okay, let me see if I understand. This would give the element in latitude and in longitude where I have my minimum value of temperature. And if I go to the temperature here and say, let me just, let me change here for
Exactly, you do it the other way around, right? You're going to apply that index on the temp 0.5 and it should match, right?
I'm sorry, I think your connection cut out a little bit. Can you repeat that, please?
So if you apply the index that it returns to temp 0 to 5, you will actually get the minimum value.
Yes, yes,
Okay.
correct, yes. So are we together, all together? Yes, okay, so now I did this for minimum and maximum values and for both products here. And now I'm extracting the values of the coordinates. Now I don't want the elements, the index. I want the values, but I'm gonna use those index that I generated here. So here I'm taking only my values, okay? The values of latitude and longitude for maximum and minimum values of temperature for both products. I'm gonna let you take a look and tell me if something doesn't look good. Okay? Are we together? Give me a thumbs up or not. I can see you now. Yes, more or less. Okay, so let us go again. Until here, we are all together, right? Because we get the index in longitude and latitude that I find the values of temperature, the minimum and maximum, okay? But on the bottom here, I'm using these indexes to find the values of my latitude and longitude. Okay, the same thing that I showed you. We have 4 elements in depth. What is the 4th element? And we saw there was 3.8 something. Okay, so that's what we are doing here. We are getting the values of latitude and longitude for each point of temperature, maximum and minimum for both products. Okay, is it better? Okay. And now I'm just printing the results. I'm asking Python to print the results for me, and I can do it, make it pretty like this. So the minimum temperature for 0.25 degrees is the minimum, the variable I created at latitude and longitude, and the variables I created here and here, here and here. So what it gives to me, it's a very pretty 4 statements of where can I find my minimum and maximum temperature. Okay. So far, so good. I'm just printing out the results that I got. Okay. And it's a good way to test the things you're doing as well. Okay. If you print the results. Okay. So let's just go over a little bit here. So, I put the both of minimums and let me just do something here. Let me see if it's gonna work. Just to add my space. Okay, now it's better. So both minimum temperature values, okay, you can see already the difference. Like I said, it's not a very big difference, but you can see difference in value and in location. And that's related to the horizontal resolution differences that we have. Same thing for maximum temperature, okay? It's very close, but it's not exact, which is good. But because we expected that, you know, they're located in different regions because the grids are different. So the equations of the models are um, being calculated in different places and in more places here than here on the map, like we saw yesterday, right? Okay, so far so good. Okay. All right, so we have, let me see, a little bit more to see. Maybe I'm gonna ask you to take our big break now, so we can get back here in 1 hour. Yes. Okay. Okay, I'm gonna stop recording